Look at the clock on your wall. The second hand moves forward, and you assume it has always moved forward, that time itself is a river flowing from somewhere into somewhere else. Behind that simple tick lies a question physicists have wrestled with for a century, a question that fractures the meaning of the word before. There may be no upstream. There may be no river. Only a shoreline where time itself begins, and beyond it, something stranger than nothing. Tonight, we will descend through every layer of what physics knows, suspects, and cannot reach. From the observable universe back to the singularity, through inflation and quantum geometry, into the competing visions of what may have existed before existence, and discover why the question itself may be the most profound object in the cosmos. Before we dive in, if you love exploring the deep mysteries of time and the cosmos as much as we do, take a second to like the video or subscribe and tell me where you're listening from and what time it is. Now, let's begin. There is a question so old and so simple that children ask it without embarrassment, and so difficult that the greatest physicists in history have spent their careers circling it without resolution. It is not a question about black holes or dark matter or the fate of stars, though all of those things are woven into its answer. It is 3 words. What came before? Before the Big Bang. Before the first light. Before the first particle. Before the first moment of anything at all. You might assume that science has an answer, or at least a well-defined approach to finding one. You might imagine that cosmologists armed with the most precise instruments humanity has ever built, with mathematical frameworks of breathtaking elegance, with satellites that have mapped the oldest light in the universe down to the finest temperature fluctuation, have at least a working hypothesis, a leading candidate, something they can point to and say, here, this is what was there. The truth is stranger. And the strangeness begins not with the answer, but with the question itself. Because here is what almost nobody tells you when this topic comes up in popular science. The question, what was before the Big Bang, may not be a question about events that happened before a threshold in time. It may be a question about the nature of time itself. It may be asking whether the word before, a word so familiar to your mind that you use it without thinking dozens of times a day, has any meaning at all when applied to the origin of the cosmos. That is not a dodge. That is not a way of avoiding the question. That is the actual frontier of physics. The point at which our best tools dissolve, where language fails, where mathematics breaks apart into singularities, and where the honest answer is, we do not know, and we may be constitutionally incapable of knowing, not because we are not clever enough, but because the information simply does not exist in any form that can reach us. This is where we are going, not around the question, but through it. And to get there, we need to start at the beginning, which is, as it turns out, an extraordinarily strange place to start. Pause here for a moment before we descend. Think about what you actually mean when you ask what came before something. You mean there was a state of affairs, and then a different state of affairs, and the first one preceded the second. You are invoking time. You are assuming that time is the medium in which before and after can exist. You are assuming that time is the kind of thing that stretches backward indefinitely, that if you could rewind the universe like a tape, the tape would never run out. This assumption feels so obvious that it barely registers as an assumption at all. It is baked into every sentence you have ever spoken about sequence and causation and history. It is baked into your nervous system, which experiences the present moment as a knife edge between the remembered past and the anticipated future. It is, in the deepest sense, the structure of your consciousness, and it may be completely wrong when applied to the universe as a whole. This is the first revelation of our descent, and it comes not from obscure speculation, but from the best tested physical theory in history. Albert Einstein published his general theory of relativity in 1915, after a decade of extraordinarily difficult work. General relativity is a theory about gravity, but it is also, and perhaps more profoundly, a theory about space-time. The key word is that, space-time, not space and time as separate things. In Einstein's framework, space and time are woven together into a single four-dimensional fabric, and that fabric is not a passive backdrop against which events unfold. It is itself a physical thing. It can bend, it can stretch, it can curve. And the presence of matter and energy is what curves it. Gravity is not a force in the traditional sense, but the geometry of bent space-time. This has an immediate and radical implication for our question. If space-time is a physical thing, something that can be created, shaped, and potentially destroyed, then it did not necessarily exist before the Big Bang. Space and time might be features of our universe. They might have come into being with the universe, or more precisely, as the universe. They might be the universe, in a certain sense. The textbook version of the Big Bang, as it is taught in classrooms and described in popular science books, tends to describe it as an explosion that happened at a specific time, at a specific place. The universe was very small and very hot, and then it expanded. This is correct as far as it goes, but it contains a subtle and profound misleading element. It implies that before the Big Bang, there was a before, a moment of before, a region of empty space into which the explosion occurred. Neither of those things is true. The Big Bang was not an explosion into pre-existing space. It was the beginning of space. It was not an event that occurred at a particular point in pre-existing time. It may have been the beginning of time. There was no outside and no earlier, because outside and earlier are spatial and temporal concepts, and space and time were themselves part of what began. If this seems abstract, consider the analogy that physicists often reach for, the surface of the Earth. Stand anywhere on the planet and ask, what is south of the South Pole? The question feels meaningful. South is a direction, and you can always go south. But at the South Pole, the concept of south runs out. Every direction from the South Pole is north. There is no south of the South Pole, not because there is a wall there, not because something stops you, but because the geometry itself no longer supports the concept. South of the South Pole is not a location you are forbidden from reaching. It is a phrase without a referent. The same logic, applied to time at the moment of the Big Bang, gives you the most basic version of what physicists call a no-boundary universe. Ask, what was before the Big Bang? And you may be asking, in the deepest sense, what is south of the South Pole? This is not the end of the story. In fact, this is barely the beginning. Because the analogy, while useful, conceals as much as it reveals. And because general relativity, for all its genius, is known to be incomplete. It breaks down precisely at the moment we most need it, at the very first instant of the Big Bang, where densities become infinite and the mathematics collapses into a singularity. A singularity, in physics, is not a physical object. It is a sign that your theory has reached the edge of its domain. It is the equation's way of saying, I cannot tell you what happens here, so we need to go deeper. We need to ask not only what general relativity says about the beginning of time, but what happens when we try to incorporate quantum mechanics, the other great pillar of modern physics, into the story. And that, as we will see, opens a landscape of possibilities that is simultaneously more hopeful and more vertiginous than anything general relativity alone could suggest. But to appreciate why that landscape matters, we need to build the foundation more carefully. We need to understand what we actually know about the early universe, how we know it, and exactly where our knowledge ends and genuine uncertainty begins. Take stock of where we are. We have a universe that is 13.8 billion years old. We have measured this with extraordinary precision, using multiple independent methods: the cosmic microwave background, the distribution of galaxies, the measured expansion rate, the ages of the oldest stars. These measurements converge with remarkable agreement. The universe had a beginning, or at least what we experience as the universe had a beginning, approximately 13.8 billion years ago. We can see back across most of that time. When astronomers point powerful telescopes at the most distant corners of the observable sky, they are not just looking across space. They are looking back through time, because light takes time to travel, and the light from distant galaxies was emitted long ago. The James Webb Space Telescope, operating from its orbit around the second Lagrange point, about 1.5 million kilometers from Earth, has captured images of galaxies that formed when the universe was only a few 100 million years old. It is the closest thing humanity has to a time machine. But there is a wall we cannot see past. Not a physical wall, a light wall. The universe, in its earliest moments, was a plasma, a dense, hot fog of charged particles so thick that photons could not travel freely through it. Light was trapped, scattered, absorbed, re-emitted. The universe was opaque. This fog persisted for roughly 380,000 years after the Big Bang. Then, as the universe expanded and cooled enough for electrons to combine with protons and form neutral hydrogen atoms, the fog lifted. Photons were suddenly free to travel. They have been traveling ever since, and we can detect them today as a faint glow of microwave radiation permeating the entire sky. This is the cosmic microwave background, or CMB. The CMB is the oldest light in the universe. It is the surface of last scattering, the moment when the universe first became transparent, and it represents a fundamental observational horizon. We cannot see beyond it using photons, because beyond it the universe was opaque. The Big Bang itself, the first fraction of a second, the inflationary epoch, the Planck era, all of this lies behind the CMB wall, inaccessible to optical or radio astronomy. This is a fact worth dwelling on. It is not merely a practical limitation that will be overcome with better telescopes. It is, in a profound sense, a structural feature of our observational access to the cosmos. We are sitting inside a bubble of observable universe, a sphere roughly 93 billion light-years in diameter, defined by how far light has had time to travel since the Big Bang. And within that bubble, we can see back to 380,000 years after the beginning, but no further using light. However, and this is one of the most extraordinary scientific achievements of the last century, we do have ways of probing the universe before the CMB wall. Not directly, but through the imprints that the early universe left on the light we can see. The CMB is not perfectly uniform. It has temperature fluctuations, tiny variations of roughly 1 part in 100,000 that encode information about the quantum processes that operated in the first fractions of a second after the Big Bang. The pattern of these fluctuations carries a signature of cosmic inflation, an extraordinary episode of exponential expansion that, according to our best current models, occurred when the universe was perhaps 10 to the power of negative 36 seconds old. Think about that number for a moment. 10 to the negative 36 seconds. A trillion is 10 to the 12th. A quadrillion is 10 to the 15th. 10 to the negative 36 is inconceivably small. And yet, within that sliver of time, the universe is thought to have expanded by a factor of at least 10 to the 26th, expanding from something smaller than a proton to something roughly the size of a grapefruit, in a blink that has no analog in ordinary human experience. Cosmic inflation was proposed by physicist Alan Guth in 1981, working at the Stanford Linear Accelerator Center at the time, as a solution to several puzzling features of the observable universe. Why is the universe so remarkably uniform in temperature across regions that, without inflation, could never have been in causal contact? Why is the large-scale geometry of space so close to perfectly flat? Why don't we see exotic relics from the early universe that our theories predict should have been produced? Inflation answered all of these questions in a single stroke by positing that the universe underwent a brief but violent period of exponential expansion driven by a hypothetical field, the inflaton field, which briefly dominated the energy budget of the early cosmos before decaying into the hot plasma of the standard Big Bang. The predictions of inflation, specific patterns in the CMB, a particular spectrum of density fluctuations, have been tested and largely confirmed by satellite missions, including WMAP, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite, operated by the European Space Agency. Planck's full-sky CMB maps, produced between 2009 and 2013, matched the predictions of inflationary models with extraordinary precision. But here is where the story opens up in ways that are both exciting and destabilizing. Because inflation, almost immediately after its proposal, was found to lead somewhere unexpected, somewhere profound, somewhere that directly bears on the question of what came before the Big Bang. If inflation happened, and the evidence suggests it did, then in most versions of the theory, it did not happen uniformly everywhere. It happened in patches. Some regions stopped inflating sooner than others. In the regions that stopped, universes like ours formed. In the regions that kept going, inflation continued, and those regions spawned further bubble universes, each with its own properties, its own physics, potentially its own constants of nature. This is eternal inflation, a concept first introduced by Paul Steinhardt in 1983, shown to be generic by Alexander Vilenkin at Tufts University, and further developed in chaotic inflation form by Andre Linde at Stanford University in 1986. It implies something extraordinary. Our Big Bang was not the only one. It was one of an endless cascade of Big Bangs, embedded in a larger eternal inflationary spacetime that had no beginning. Eternal inflation pushes the question of what came before the Big Bang into a larger context. It says, before our Big Bang, there was an eternally inflating void, seething with quantum fluctuations, spawning universes in an endless chain. There was no first moment. There was no single creation. There was just the ongoing process without beginning or end. This sounds like it answers the question. It sounds like it fills in the blank. Before our Big Bang, there was the inflationary multiverse. Problem solved. But here's what that answer doesn't account for. Here's where the apparent simplicity of eternal inflation solves it breaks down. In 2003, physicists Arvin Border, Alan Guth, and Alexander Vilenkin published a rigorous mathematical proof that has become one of the most important and least widely known results in cosmology. The Borde-Guth-Vilenkin theorem, as it is now called, demonstrates that any spacetime that is expanding on average, even an eternally inflating one, must be geodesically incomplete in the past. In plain language, even eternal inflation cannot extend infinitely into the past. Even an inflationary multiverse has a past boundary. Even the most expansive model of before has a beginning. The theorem does not tell us what that beginning was. It does not say there was a singularity. It says only that the inflationary space-time cannot be past eternal, that by tracing any path backward through an eternally inflating universe, you will eventually reach a point where the path simply stops, where space-time itself has an edge. What lies beyond that edge? What came before the inflationary multiverse? What was there before the thing that was before the Big Bang? This is the genuine frontier, and it is here, at this recursive and vertiginous boundary, that the most daring theoretical ideas in modern cosmology are competing for the right to answer a question that may not have an answer. Anaphora is the rhythm of deep time. It could have been one thing. It could have been nothing. It could have been something so unlike anything we have words for that every description we reach for is already wrong. We are going to spend the rest of this exploration examining what our best theories actually say about these possibilities. We are going to go layer by layer, from the edge of observation inward toward the Planck scale, outward into the rival cosmologies, and finally to the place where physics meets the question it cannot answer. Each layer will reframe what came before it. Each scale will reveal new strangeness. The universe, it turns out, does not have a simple story. It has a story that deepens every time you look more carefully. And the deepest mystery is not at the end of the story. It is at the very beginning, which may not have been a beginning at all. Take stock of where we are before the descent continues. We have established the basic frame, a universe 13.8 billion years old, observable back to 380,000 years after its beginning, through the cosmic microwave background, and theoretically traceable, through inflation, back to the first tiny fractions of a second. We have established that general relativity, our finest theory of space and time, treats space-time not as a pre-existing stage, but as a physical entity that may have come into being with the universe itself. And we have established that the question, what came before, may be, in its most naive form, a category error, like asking what is south of the South Pole. But we have also established that the story does not end there, because category errors can be resolved, and when they are resolved, they often give way to deeper questions rather than simpler answers. And because the physics of the very early universe, inflation, quantum cosmology, the Planck regime, does not give us a clean nothing before, everything after. It gives us a thicket of extraordinary possibilities, each with its own implications, each supported by different strands of evidence and mathematical reasoning, and none yet decisive. Now we descend more deliberately. We go layer by layer through what physics actually proposes. The first layer, the one closest to firm ground, is the standard model of the Big Bang itself, not as a cartoon of an explosion, but as a rigorous description of the earliest moments for which we have reliable physics. Understanding this layer is essential, because it is precisely where this layer breaks down that the interesting questions begin. Everyone knows that the Big Bang is where the universe started. The textbook answer is straightforward. Everything we can observe began in an extraordinarily hot, dense state roughly 13.8 billion years ago, and has been expanding and cooling ever since. This picture is confirmed by multiple lines of evidence. The expansion of the universe published by Edwin Hubble in 1929, from observations at the Mount Wilson Observatory in California, the CMB discovered by Arno Penzias and Robert Wilson, and published in 1965 from work at the Bell Telephone Laboratories facility at Crawford Hill in Holmdel, New Jersey, and the specific abundances of light elements like hydrogen and helium that match the predictions of Big Bang nucleosynthesis with extraordinary precision. That picture is almost entirely right. And yet, the moment you look closer, it becomes strange. The standard Big Bang model, based on Einstein's general relativity applied to a uniformly expanding universe, describes the early cosmos with remarkable fidelity from about 1 second after the beginning onward. 1 second in, the universe was a hot plasma of protons, neutrons, electrons, neutrinos, and photons, with a temperature of roughly 10 billion degrees. The physics of that moment, nuclear physics, particle physics, thermodynamics, is the same physics we test in laboratories on Earth, and it works. The predictions match the observations. Go earlier. Go back to 1 microsecond, 1 millionth of a second, and the temperature was 1 trillion degrees. At that energy, protons and neutrons themselves dissolve into their constituent quarks and gluons. We have probed this regime in particle accelerators, particularly at CERN's Large Hadron Collider in Geneva, Switzerland, where collisions briefly recreate conditions approaching those of the universe at this epoch. The physics here is harder, but still understood. Go earlier still. To the electroweak epoch, a tiny fraction of a second after the bang, when the electromagnetic force and the weak nuclear force were unified into a single electroweak force. To the GUT epoch, at around 10 to the power of negative 36 seconds, when the strong nuclear force may have been unified with the electroweak force, and when inflation is thought to have occurred. The physics here is theoretical. We have no particle accelerator that can probe these energies, but the mathematical framework is consistent and makes testable predictions that align with what we observe in the CMB. And then, before all of that, at the Planck time, 10 to the negative 43 seconds, the smallest meaningful interval of time in physics, general relativity collapses. The equations produce infinities. The space-time geometry becomes chaotic and undefined. Quantum fluctuations in space and time become so violent that the very concept of a smooth space-time background dissolves. This is the Planck wall, and it is the true boundary of our theoretical knowledge. Everything before the Planck time is, in the strictest sense, beyond the reach of any theory we currently possess. The Planck time is named for Max Planck, the German physicist who in 1900 first proposed the quantization of energy, the foundational insight of quantum mechanics. The Planck units are a set of natural units built from the 3 fundamental constants that govern the regime where quantum mechanics and gravity intersect: the speed of light, the gravitational constant, and Planck's own constant. They represent the scale at which quantum gravitational effects become dominant, where you cannot ignore either the quantum nature of matter or the curvature of space-time. And we have no theory that correctly describes both simultaneously. This is not a minor gap. This is the central unsolved problem of theoretical physics. Quantum mechanics and general relativity are, each in their own domain, the most precisely confirmed theories in the history of science. But they are mathematically incompatible. They describe reality using completely different languages. Quantum mechanics is a theory of discrete, probabilistic events, particles that exist in superpositions of states, wave functions that evolve according to the Schrödinger equation, measurements that collapse possibilities into actualities. General relativity is a theory of smooth, continuous geometry, space-time as a manifold, gravity as curvature, deterministic evolution described by Einstein's field equations. Put them together near the Planck scale and the mathematics breaks. Infinities cascade. predictions become meaningless. The theory ceases to function. What this means for our question is stark. Whatever happened at or before the Planck time, and whatever came before the Big Bang in any meaningful sense, lies in a regime where we have no working theory. We are not approaching the answer to what came before with well-tested physics. We are approaching it with bold, beautiful, mathematically serious, but observationally unconfirmed hypotheses about quantum gravity, about the nature of space-time at its most fundamental level. We are doing theoretical physics at the frontier, where the maps run out. This is worth stating clearly, and it is worth sitting with. It is not a failure of science. It is science behaving exactly as science should, identifying the boundary of what is known, naming that boundary precisely, and proposing testable, or at least mathematically coherent, ideas about what lies beyond. The proposals are remarkable, and they divide broadly into several families, each with a different vision of what before the Big Bang could possibly mean. The first family says, there was nothing. The universe emerged from nothing, not in the trivial sense that nothing is just empty space, because empty space in quantum mechanics is not nothing, as we will see, but in a genuine philosophical sense. No space, no time, no laws, no prior state. This sounds like the most radical position, but it may actually be the most parsimonious, and it has serious mathematical defenders. The second family says, there was something, but something so different from our universe that calling it a before requires redefining the word. Time itself may have been different, or may not have existed as a dimension at all. The geometry of space-time may have been Euclidean rather than Lorentzian, which is to say that time behaved more like a spatial direction than the temporal arrow we experience. In this view, asking what came before the Big Bang is like asking what is north of the North Pole. Not because there is nothing there, but because the question applies a directional concept to a geometry that does not support it. The third family says there was a prior universe, or a series of prior universes connected to ours through a bounce, a cycle, or a transition. The Big Bang was not a true beginning, but a transition, perhaps from a contracting universe to an expanding one, perhaps from one aeon of cosmic history to the next, perhaps from a quantum predecessor state to the classical cosmos we inhabit. In this view, before is a perfectly meaningful word, and it points to a universe that existed before our own. Each of these families contains multiple specific theoretical proposals. Each is internally consistent. Each makes different predictions, some testable, some not. And each, when you look closely, reveals its own layer of hidden complexity. Consider the second family first, because it is the one most directly rooted in established physics, or at least in a well-motivated extension of it. This is the territory of the Hartley-Hawking no-boundary proposal. In 1983, physicists James Hartle at the University of California, Santa Barbara, and Stephen Hawking at Cambridge University jointly proposed what has become the most famous idea in quantum cosmology. Their proposal takes seriously the implications of quantum mechanics for the very beginning of the universe. In ordinary quantum mechanics, we describe a particle's state using a wave function, a mathematical object that encodes the probabilities of finding the particle in different positions or with different momenta. Richard Feynman showed that the wave function of a particle can be computed by summing over all possible paths the particle could have taken, a procedure called the path integral, or sum over histories. Every possible path contributes. The interference between these contributions produces the quantum behavior we observe. Hartley and Hawking applied this idea to the entire universe. They asked, what is the wave function of the universe? How do we compute the quantum state that describes the cosmos as a whole? And they proposed a specific prescription: compute the wave function by summing over all possible space-time geometries that have the observed universe as their boundary, but that have no other boundary, no initial boundary, no edge in the past. The universe's boundary condition is that it has no boundary. The key technical ingredient of the Hartley-Hawking proposal is imaginary time. In ordinary physics, time is a real number. It ticks forward, and the equations of motion are formulated in terms of how things change as real time advances. But there is a mathematical trick called a Wick rotation, after the Italian physicist Giancarlo Wick, who developed it, in which you replace real time with imaginary time. Time multiplied by the square root of -1. When you do this, the mathematical structure of time becomes indistinguishable from a spatial dimension. Space-time becomes Euclidean, 4 spatial dimensions, rather than Lorentzian, 3 spatial and 1 temporal. In Euclidean space-time, there is no privileged time direction. There is no arrow of time. There is no before and after in the usual sense. And there is, crucially, no singularity at the beginning. The Big Bang singularity, which in Lorentzian space-time represents a point where the density becomes infinite and the equations break down, becomes in Euclidean space-time a smooth, rounded-off region, like the south pole of a sphere. No edge, no boundary, no singular beginning. Hawking described this with characteristic economy. He wrote that events before the Big Bang are simply not defined because there is no way one could measure what happened at them, and that time began at the Big Bang in the same way that a line of latitude begins at the South Pole. It is not that there is a wall there. It is that the question of what came before dissolves when you understand the geometry correctly. The no-boundary proposal is, in its own terms, beautiful. It is arguably the most elegant answer to the question of what came before. The question is malformed because in the correct mathematical description of the quantum universe, there is no before. There is only the smooth Euclidean geometry from which the Lorentzian universe, with its arrow of time and its experience of before and after, emerges as a kind of large-scale classical approximation. But the no-boundary proposal faces serious problems, and the scientific community is genuinely divided on whether it works. Some researchers think it is profoundly correct, that it is the only mathematically self-contained description of the universe's initial conditions, that it avoids all the philosophical problems associated with the cause of the universe, and that it makes specific predictions about the CMB that can, in principle, be tested. Others think it fails on technical grounds, that when you try to compute the path integral Hartley and Hawking prescribed with mathematical rigor, the sum over histories does not converge or gives wrong answers. In 2017 and 2018, physicist Neil Turok at the Perimeter Institute in Dash, Waterloo, Canada, and his collaborators published papers arguing that a careful calculation of the no-boundary path integral predicts that the universe should be extremely inhomogeneous and irregular, precisely the opposite of what we observe. This controversy has not been resolved. Hartley and Hawking's collaborators and other defenders of the proposal dispute Turok's calculations and argue that with the correct mathematical prescription, the no-boundary wave function does predict a smooth, expanding universe like ours. The debate involves difficult and contested mathematics, the behavior of path integrals in complex space-time geometries, the interpretation of quantum amplitudes, the choice of contours in the complex plane. These are not questions with obvious answers. Something here deserves attention. The no-boundary proposal is not a theory about something that happened before the Big Bang. It is a theory about why the concept of before does not apply. This makes it uniquely difficult to test. You cannot look for evidence of what came before if the theory says there was no before. The proposal's predictions are primarily about the state of the universe at the beginning, the initial conditions, rather than about any prior state. And initial conditions are, by definition, hard to test. They are the starting state from which everything else follows, and many different initial conditions can lead to similar-looking universes. So the no-boundary proposal is alive, contested, beautiful, and not definitively confirmed or refuted. It represents the most internally consistent answer to what came before, because its answer is that the question is ill-posed, but it is not the only serious idea on the table. Now we turn to the third family of proposals, the cyclic and bouncing cosmologies. These represent a fundamentally different philosophical stance. They take seriously the possibility that before is a meaningful word, that time did extend before the Big Bang, and that what existed before was another universe, or another phase of this one, connected to our beginning through some kind of cosmic transition. The oldest and simplest version of this idea is the cyclic universe, a cosmos that expands from a Big Bang, eventually stops expanding, and begins to contract under its own gravity, collapses back to an infinitely dense state, and then, in a big bounce, expands again. Expand, contract, bounce, expand, contract, bounce. The universe oscillating through infinite cycles, with no beginning and no end, only an eternal rhythm. This idea has ancient roots in Hindu cosmology, in the thinking of early Greek philosophers, and it has been periodically revived by modern physicists. It is appealing in its symmetry and its avoidance of a true beginning. But in its naive classical form, it has a fatal problem, the second law of thermodynamics. Entropy, the measure of disorder in a physical system, always increases. In each cycle, the universe accumulates more entropy. Reverse the arrow of time, and each cycle must have started with less entropy than the one before. Trace the sequence backward, and you eventually reach a cycle of zero entropy, a pristine, ordered beginning. The cyclic universe, naively conceived, merely pushes the question of the beginning back into the past. Modern cyclic proposals try to solve this problem with more sophisticated physics. The most mathematically developed contemporary bouncing cosmology emerges from a framework called loop quantum cosmology, or LQC, an approach to quantum gravity developed primarily by physicist Abhay Ashtekar at Pennsylvania State University and his collaborators. In loop quantum cosmology, the Big Bounce was first rigorously derived in February 2006 for isotropic and homogeneous models by Abhay Ashtekar, Tomasz Pawlowski, and Parampreet Singh at Pennsylvania State University. Loop quantum gravity, on which LQC is based, is a candidate theory of quantum gravity that takes a radically different approach from the more famous string theory. Rather than positing that fundamental particles are vibrating strings in extra dimensions, loop quantum gravity proposes that space itself is quantized, that it has a discrete, granular structure at the Planck scale, built from tiny loops of quantum geometry. Space-time in this framework is not a smooth continuum, but a network of interconnected quanta, each contributing to the fabric of reality. When this quantized geometry is applied to the cosmological setting, something extraordinary happens at the point where classical general relativity would predict a singularity. Quantum geometry creates a brand new repulsive force, which is totally negligible at low space-time curvature, but rises very rapidly in the Planck regime. overwhelming the classical gravitational attraction and thereby resolving singularities of general relativity. The classical Big Bang singularity, rather than being a wall beyond which physics breaks down, is replaced by a quantum bounce, a moment of maximum density at which the universe reaches roughly the Planck density, on the order of 10 to the 96th kilograms per cubic meter, and then rebounds. The contraction of a predecessor universe is reversed, not by a physical bounce in the colloquial sense, but by a quantum mechanical repulsion that becomes dominant when space-time geometry is compressed to its minimum grain size. What this means is profound. Research in loop quantum cosmology purports to show that a previously existing universe collapses not to a singularity, but to a point where the quantum effects of gravity become so strongly repulsive that the universe rebounds back out, forming a new branch. Our Big Bang in this picture was not a creation ex nihilo. It was the rebound of a prior collapsing universe, whose entire history, its expansion, its cooling, its formation of structures, its eventual recontracting, preceded our own. The word before applies in the most literal sense. There was a universe before ours, and the Big Bang was the moment of its transformation into us. This is a testable idea, at least in principle. Loop quantum cosmology makes specific predictions about the large-scale structure of the universe, about the power spectrum of density fluctuations in the CMB, about the abundance of primordial gravitational waves. LQC can modify the form of primordial cosmological perturbations, for example by reducing power at large scales in inflationary models, or by suppressing the tensor-to-scalar ratio in the matter bounce scenario. These two effects are potential observational tests for loop quantum cosmology. Future observations, particularly detailed measurements of the polarization of the CMB and the detection of primordial gravitational waves, may be able to distinguish between LQC predictions and those of standard inflation. There are caveats. The loop quantum cosmology bounce has been demonstrated rigorously in simplified symmetric models of the universe. While the existence of the big bounce has still to be demonstrated from loop quantum gravity, the robustness of its main features has been confirmed using exact results and several studies involving numerical simulations using high-performance computing. Whether the bounce survives in the full, messy, anisotropic universe, with all its complicated structure and asymmetries, remains an open question. Some researchers argue that the bounce is robust and will persist in more general settings. Others argue that anisotropies grow so rapidly during contraction that they dominate the dynamics long before the Planck density is reached, preventing a clean bounce. Some researchers think the bounce is a universal feature of quantum gravity, inevitable wherever the classical singularity would otherwise appear. Others think it is an artifact of the specific model studied and will not survive in a more general treatment. We genuinely do not know. This is one of the explicit uncertainty admissions that cosmology must make. The loop quantum bounce is mathematically compelling and internally consistent, but its behavior in realistic cosmological settings has not been fully established. Now consider a different cyclic vision, one that emerges not from loop quantum gravity, but from a completely different direction. In 2010, the mathematician and physicist Roger Penrose published his Conformal Cyclic Cosmology, or CCC, in a book called Cycles of Time. Conformal cyclic cosmology is a cosmological model in the framework of general relativity proposed by Penrose, in which the universe iterates through infinite cycles, with the future time-like infinity of each previous iteration being identified with the Big Bang singularity of the next. The key word in Penrose's proposal is conformal. Conformal geometry is a branch of mathematics that studies shapes and structures that are preserved under changes of scale. A conformal transformation can stretch or compress distances, but it preserves angles. The local geometry remains the same, even as the overall scale changes. Penrose's insight is that the far future of our universe and the very beginning of the next universe are, in a certain mathematical sense, conformally equivalent. Here is why. The very early universe is smooth. The universe right now is lumpy, with stars and galaxies and black holes all over the place. But the future universe will be smooth again. Black holes will evaporate, and the cosmological constant will disperse all matter, leaving us nothing but empty space. In the very far future, after an almost incomprehensible span of time, something like 10 to the 100th power years, all the black holes in the universe will have evaporated through Hawking radiation, all the matter will have dispersed, and the universe will be an essentially empty, cold, featureless expanse of space, dominated entirely by dark energy. And in this far future, Penrose argues, the geometry of the universe loses track of scale. Without massive particles to define rods and clocks, the distinction between large and small becomes meaningless. The universe becomes conformally smooth. At the end of an aeon, space-time becomes conformally smooth, and a new aeon begins. CCC avoids a singularity at the Big Bang, providing a naturalistic explanation for the universe's initial conditions. Penrose argues that the conformal smoothness of space-time at the end of one aeon leads to the conditions necessary for the low entropy start of the next aeon. This is Penrose's answer to the entropy problem that plagues naive cyclic models. He is not proposing that the universe contracts and bounces, accumulating entropy with each cycle. He is proposing that entropy itself is effectively reset at the transition between aeons, that the vast sea of entropy in the dying universe, distributed uniformly across expanding space, becomes the low entropy smooth beginning of the next universe through the mathematical magic of conformal rescaling. The end and the beginning are, in this sense, the same geometric object, looked at from different perspectives. Penrose and his collaborators have searched for observational evidence of CCC in the CMB. Penrose and collaborators have claimed to identify evidence for CCC in the CMB. They suggest that concentric circular patterns in the CMB could be imprints from previous aeons. These Hawking points, as Penrose calls them, would represent the remnants of black hole evaporation events in the prior aeon, faint rings of slightly elevated temperature in the cosmic microwave background. In 2025, Penrose and collaborator Christoph Meissner published a new paper refining the physics of the crossover between aeons, introducing a mechanism involving gravitational waves to explain how the transition can occur smoothly. But the claimed CMB evidence is deeply contested. Researchers find that spots consisting of a few unusually bright or dark pixels erroneously lead to regions with many low-variance circles when applying the search criteria used in previous work. After removing those spots from the data, no statistically significant low-variance circles can be found. The community remains split. Some regard Penrose's CCC as a brilliant but unsubstantiated speculation. Others see it as a physically motivated framework whose observational predictions are genuinely being tested by current and future CMB experiments. There is something beautifully strange about CCC that deserves a pause. It proposes that what we call the Big Bang, the supposed beginning of everything, was not the beginning of everything. It was a crossover surface, a handshake between one vast cosmic history and the next. The last light from the dying universe of the previous aeon redshifted to infinite wavelength, became the first light of our own. What we think of as the fire of creation was, in Penrose's telling, the final exhalation of a cosmos too old and too cold to sustain any further structure. This reframes the very concept of a beginning. It also reframes the concept of an end. Our universe is not heading toward oblivion. It is heading toward another beginning. A beginning that is, from our side of the crossover, indistinguishable from death. Time, in CCC, does not have an arrow pointing from birth to death. It has an arrow that curves endlessly back into another birth. The loop, quantum bounce, and Penrose's conformal cyclic cosmology are not the only members of the third family of before proposals. There are also evaporate and cyclic models originating from string theory, particularly those developed by Paul Steinhardt at Princeton University and Neil Turok in the early 2000s. In these models, our universe is a three-dimensional membrane, a brain, floating in a higher dimensional space, and the Big Bang was the collision between two such brains. Before the Big Bang in this picture was an empty, cold, nearly featureless universe, a brain that had been expanding and cooling for an eternity until its collision with our brain released the enormous energy that we experience at the beginning of time. The evaporate scenario has the appealing feature of explaining the remarkable smoothness and flatness of our universe without inflation. The collision of cold, flat brains naturally produces a smooth, flat result. But it also faces formidable challenges, including the behavior of perturbations through the bounce and the question of whether the relevant brains and higher dimensions actually exist. We are now deep enough in our descent to see something important. Not one of these proposals, the no-boundary universe, the LQC bounce, conformal cyclic cosmology, ekpyrosis, has been observationally confirmed. Each is mathematically serious. Each is defended by brilliant physicists. Each has internal coherence. And each remains genuinely speculative. There is a further proposal we have not yet examined, one that is perhaps the most audacious of all. It comes not from loop quantum gravity or conformal geometry, but from the implications of quantum mechanics taken to their logical extreme. And it addresses not the question, what was there before, but the even more radical question, what if there was genuinely nothing, and the universe created itself from that nothing? This is the proposal associated most directly with the work of Alexander Vilenkin at Tufts University. In 1982, Vilenkin proposed that the universe could have tunneled into existence from a state of nothing, not empty space, not a prior state, but literally no space, no time, no laws of physics. He applied the quantum mechanical process of tunneling, in which a particle can pass through a barrier that classical physics would forbid it from crossing, to the universe as a whole. In Vilenkin's picture, the nothing before the universe is a state of zero energy, zero matter, zero space, zero time. And the universe emerged from this state through a quantum fluctuation, a tunneling event that requires no prior cause, no trigger, no external force. It simply happened because quantum mechanics permits, with finite probability, transitions between states that have no classical path connecting them. The appeal of this proposal is obvious. It requires no prior state. It requires no cause. It is, in a certain sense, the most truly creation from nothing scenario in theoretical physics. But it also faces the deepest philosophical challenge. Quantum mechanics, as we know it, is a theory of how things change over time. Tunneling is a process that takes time. Even if it is an indeterminate amount of time, it is a temporal process. How can you apply quantum mechanics to the creation of time itself? How can there be a probability for a transition if there is no time in which the probability can be defined? Vilenkin and others who work in this tradition argue that the quantum cosmological framework, particularly the Wheeler-DeWitt equation, which is the quantum mechanical analog of Einstein's field equations for the universe as a whole, does not actually require a time parameter. The universe's wave function satisfies the Wheeler-DeWitt equation, and that equation is timeless. It does not describe how the wave function changes over time, because time is not a fundamental parameter, but an emergent feature of certain quantum states. In this framework, before, the universe is not a temporal concept, but a mathematical one. It is the domain of the quantum amplitude, not the domain of physical events. This brings us to one of the most profound and least comfortable admissions that cosmology must make. We do not know whether quantum mechanics, as we currently understand it, even applies to the universe as a whole. Quantum mechanics was developed to describe the behavior of small systems. Particles, atoms, fields, in the context of a pre-existing space-time background. It was never designed to be applied to the entire universe, including space-time itself, as a single quantum system. Whether it can be so applied, whether the wave function of the universe is a meaningful object, whether the Wheeler-DeWitt equation is the right equation to use, all of these are open questions. Deep, genuinely open questions, not the kind that will be resolved by a single clever experiment or calculation. Some researchers think it is entirely straightforward. Of course, quantum mechanics applies to everything, including the universe, and the task is simply to work out the details. Others think this is naive, that applying quantum mechanics to the universe as a whole requires a radical revision of what quantum mechanics means, particularly regarding the role of the observer. Still, others think that the framework of quantum mechanics itself will need to be replaced or transcended before we can make sense of the universe's origin. We cannot know, and this is not a provisional "we do not know yet," but a genuine structural uncertainty about the limits of our conceptual frameworks. It may be that the question, what came before the Big Bang, cannot be answered within quantum mechanics. It may be that it cannot be answered within any extension of quantum mechanics we can currently imagine. It may require a revolution in physics of a kind that has happened only 2 or 3 times in human history. The kind of revolution that does not merely add to existing knowledge, but overthrows the fundamental categories by which we organize our understanding of reality. Stay with this for a moment. The history of physics is, among other things, a history of successful category overthrows. Newtonian mechanics seemed complete, self-consistent, a perfect description of the physical world. Until Maxwell's equations for electromagnetism implied that light was a wave in a medium that had to be absolute, and the resulting crisis led Einstein to relativity, which showed that space and time were not the absolute background Newton had assumed. Quantum mechanics seemed, for a while, like an add-on to classical physics, a description of small-scale behavior that would eventually reduce to classical results at large scales. But it turned out to be a complete reconception of what it means for a physical system to have properties at all. The quest to understand what came before the Big Bang may be the next such crisis. The questions are already forcing us to reconsider what time is, what space is, what causation means, what nothing means, and whether the universe is the kind of thing that can have a cause at all. These are not peripheral questions. They are the central questions of physics and philosophy combined, and they are being asked not in armchairs, but in the equations of some of the most technically sophisticated scientists who have ever lived. Now we turn to a domain where the strangeness deepens further. Because there is an entirely different angle on the before question, one that does not involve exotic physics of bouncing universes or quantum tunneling from nothing, but instead comes from asking a seemingly more basic question. What is the structure of time itself? Picture yourself standing in a very still room. Not a room with walls, a conceptual room, a room that represents all of physical reality. In this room, every event that has ever happened, is happening, or will happen, exists simultaneously as a point in four-dimensional space-time. The past is not gone. The future has not yet arrived. Every moment is, in the language of relativity, equally real, equally there in the space-time manifold. Physicists sometimes call this the block universe view of time. The idea that time is not a flowing river, but a fixed landscape, and what we experience as the passage of time is our consciousness moving through that landscape. In the block universe, the question, what came before the Big Bang, becomes, what is outside the boundary of our block? If the space-time of our universe is a finite four-dimensional region, with the Big Bang as one boundary and the far future as another, then the question of before is the question of what, if anything, lies beyond that boundary. And in general relativity, space-time is not a thing floating in a larger space. It is all there is. There is no outside to the block. But here is the complication. We do not know whether our space-time is a closed, finite block or an open, infinite one. We do not know whether the boundary at the Big Bang is a genuine edge of space-time, a singularity, or a smooth region where the geometry changes character. We do not know whether there are multiple blocks, connected to ours or disconnected from it. These questions are currently unanswerable, not because we lack the observational tools to resolve them, though we do, but because the mathematical framework needed to address them does not yet exist in complete form. This is the Planck wall, encountered from a different direction. No matter which approach we take to the before question, general relativistic, quantum cosmological, cyclic, inflationary, we eventually hit the same limit. The physics of the Planck era, the first 10 to the negative 43 seconds of cosmic time, is inaccessible to current theory. Any answer to what came before must pass through this wall, and we do not yet have the tools to do so. What we can do, what physicists are actively doing, is approach the wall from multiple directions, looking for consistency, for convergence, for hints of what lies on the other side. The approaches we have examined: no-boundary quantum cosmology, loop quantum cosmology, conformal cyclic cosmology, quantum tunneling from nothing, each represent a different direction of approach. And there are newer approaches still, some of extraordinary mathematical sophistication that we will examine as we continue our descent. Consider the most recently developed frontier, the application of numerical relativity to cosmological questions. A paper by FQX, cosmologist Eugene Lim of King's College London, and astrophysicists Katie Clough of Queen Mary University of London and Yosu Auracoetsia at Oxford University, published in Living Reviews in Relativity in June 2025, proposes using complex computer simulations to numerically solve Einstein's equations for gravity in extreme situations. The team argues that numerical relativity should be applied increasingly in cosmology to probe some of the universe's biggest questions, including what happened before the Big Bang, whether we live in a multiverse, if our universe has collided with a neighboring cosmos, or whether our universe cycled through a series of bangs and crunches. Numerical relativity is a computational technique originally developed to predict the gravitational waves produced by merging black holes, a prediction that was spectacularly confirmed by the LIGO detector's first detection in September 2015. The mathematics of two colliding black holes is so complex that no analytical solution exists. It can only be solved by massive numerical computation. Traditional methods require simplifying the universe to make the math manageable. But numerical relativity is built to handle the full, messy reality of Einstein's theory. As Lim puts it, you can search around the lamppost, but you can't go far beyond the lamppost where it's dark. You just can't solve those equations. Numerical relativity allows you to explore regions away from the lamppost. The proposal to apply these techniques to the birth of the universe is genuinely new, and it represents a methodological shift rather than a new theory about what came before. It is an acknowledgement that the questions are so mathematically hard that even our best analytical tools cannot reach them, and that the next generation of supercomputers may be able to do what human mathematicians cannot. This is not a satisfying answer to what came before, but it is a credible path toward eventually producing one. We have now laid out the landscape of the serious scientific proposals: the no-boundary universe of Hartley and Hawking, the loop quantum bounce of Ashtekar and colleagues, the conformal cyclic cosmology of Penrose, the tunneling from nothing proposal of Vilenkin, the ekpyrotic brain collision of Steinhardt and Turok, and the emerging frontier of numerical relativity. Each has its strengths, each has its problems. None has been confirmed, and all of them, without exception, are pushing against the same limit, the Planck scale, where our physics runs out. In the sections ahead, we are going to go deeper into each of these proposals, examining not just what they say, but why physicists find them compelling, what evidence, however indirect, bears on their plausibility, and what they would imply about the nature of time, causation, and existence if they were true. We are going to examine the deepest implications of the CMB, the oldest light we can see, for what lies beyond our observational horizon. We are going to descend into the quantum mechanics of space-time itself, into the Wheeler-DeWitt equation and what it says about the beginning of time. And we are going to examine what a small number of theoretical physicists regard as perhaps the most important and least understood concept in all of cosmology: the nature of nothing, what it means for there to be no thing at all, and whether that concept is even coherent. Because here is what lurks behind all of these proposals. Here is the thing that almost nobody who discusses the Big Bang at a casual level notices. Every proposal about what came before, even the proposal that there was nothing, must answer a prior question: why are there laws of physics at all? Why does anything obey rules? Why is there mathematics? And why does the universe follow it? Even if we could establish beyond reasonable doubt that the universe emerged from a quantum fluctuation of nothing, we would still face the question: what determined that quantum fluctuations were possible? What defined the probability distribution over possible universes? What set the laws of quantum mechanics that permitted the tunneling? You cannot tunnel without laws. You cannot have a wave function without something to describe it with. Even nothing needs to be precisely defined. And as soon as you define it precisely enough to do physics with, it stops being nothing. This is the deepest layer of the question, the one that lies beneath all the physics. And it is the layer that physics by itself may never fully reach. But that is not a reason to stop descending. It is a reason to keep going, carefully, honestly, without pretending that the maps are more complete than they are. Because even in the territory where the maps run out, the act of looking, of pushing the equations as far as they will go, of naming the places where they fail, this is itself a form of knowledge. A form of knowledge that is uniquely, profoundly human. Roughly 13.8 billion years of cosmic history lie behind us, and we have traced our way back through nearly all of it. Through the cooling of the plasma, through the first stars, through inflation, all the way to the Planck wall where our best theories dissolve. Now we turn to the proposals that attempt to pass through that wall, or to navigate around it, or to show that the wall itself is an illusion produced by our incomplete understanding of space-time. Each of the next sections descends one layer deeper. Each layer asks a harder version of the same question. What is time, and does it have an origin? Picture yourself in a room with no windows. You know the room is there because you are standing in it. You can feel the floor beneath your feet, the air against your skin. But you cannot see the walls, and you do not know how large the room is. You can walk in any direction, and for a very long time the floor will be solid beneath you. But somewhere, you do not know where, the floor ends. And beyond the edge, you have no idea what awaits. That is the situation of cosmology at the Planck scale. The floor is solid where we can test it. The edge is real. And beyond it, we have theories, beautiful, mathematically serious, physically motivated theories, but no confirmed knowledge. This section descends into the quantum nature of time, into what it actually means to say that time began, into the Wheeler-DeWitt equation, which is perhaps the strangest and most profound equation in all of physics, and into the extraordinary implication that time may not be fundamental at all. The idea that time might not be fundamental, that it might be an emergent property of something deeper, something that is itself timeless, is not a fringe speculation. It is taken seriously by a significant number of physicists working at the intersection of quantum mechanics and gravity. And understanding why requires understanding what happens when you try to write down a quantum theory of the universe as a whole. In ordinary quantum mechanics, you describe a system using a wave function that evolves over time. The Schrödinger equation tells you, given the wave function now, here is the wave function a moment later. Time is the parameter with respect to which the wave function evolves. It is the background against which quantum events unfold. But what happens when the system you are describing is the entire universe, including space and time themselves? There is no external clock to measure the passage of time. There is no observer outside the universe to watch the wave function evolve. Time is not a background. It is part of what you are trying to describe. And this creates a profound problem, one that was identified in the late 1960s by physicists Bryce DeWitt at the University of North Carolina at Chapel Hill and John Wheeler at Princeton University, whose attempts to quantize gravity led to an equation of disturbing simplicity and even more disturbing implications. The Wheeler-DeWitt equation describes the quantum state of the universe using a wave function, a function of the geometry of space and the matter fields within it. It is, in this sense, the quantum mechanical equation of motion for the cosmos. But here is what makes it unlike any other equation in physics. It has no time derivative. In the Schrödinger equation, the left-hand side involves the rate of change of the wave function with time. In the Wheeler-DeWitt equation, time has disappeared. The equation says, in essence, that the wave function of the universe does not change. It is static, frozen, eternal. This is what physicists call the problem of time in quantum gravity, and it is one of the deepest unsolved problems in all of theoretical physics. Consider what this means. If the Wheeler-DeWitt equation is correct, and it is, at minimum, the most natural equation you can write down when you try to quantize general relativity, then the universe's wave function does not evolve. The universe, at the most fundamental level of quantum description, is timeless. What we experience as the flow of time as the passage from moment to moment, as the difference between past and future, is not written into the fundamental equation. It must emerge from the quantum state in some other way. How can a timeless equation give rise to the experience of time? Several approaches have been proposed. The most elegant and perhaps the most deeply strange is the relational approach to time, developed in part by the Italian physicist Carlo Rovelli. The key insight is this: time, in our experience, is not an absolute external parameter. It is something we infer from the relationships between physical systems. A clock does not measure time itself. It measures its own evolution relative to other things in the universe. The hands of a clock move relative to the clock's mechanical parts, which move relative to the electromagnetic forces holding them together, which evolved in a universe that has expanded and cooled from the Big Bang. Time, in this view, is the ordered correlation between physical systems. The fact that when System A is in state X, System B tends to be in state Y, and when A is in state X prime, B tends to be in state Y prime. In the relational picture, the Wheeler-DeWitt equation's lack of a time variable is not a deficiency. It is a feature. It reflects the fact that the universe, taken as a whole, does not evolve in time, because there is nothing outside it for it to evolve relative to. Within the universe, subsystems evolve relative to each other, and this relative evolution is what we call time. But the universe as a whole is frozen in a kind of eternal quantum superposition. If this is right, and it is contested, genuinely contested, with serious physicists on both sides, then asking what came before the Big Bang is asking about the temporal history of a system that, at its most fundamental level, has no temporal history. The question applies a concept, temporal sequence, that is emergent and approximate to a domain where it has no foundation. This is different from the Hartley-Hawking answer, which says the question is malformed because of the geometry of space-time near the beginning. The Wheeler-DeWitt/relational time answer says the question is malformed because time itself is not a fundamental ingredient of reality. They arrive at similar destinations. The question cannot be answered as posed, but by completely different routes. Both cannot be simultaneously correct in their details because they invoke different physical frameworks. But they share a profound philosophical implication that the human concept of before may be, at the deepest level of physical description, simply inapplicable. Not wrong in the way that a false statement is wrong, but inapplicable in the way that what color is jealousy is inapplicable, a category error of the most fundamental kind. Anaphora is the heartbeat of this realization. Time may not be what we think it is. Time may not be what it feels like. Time may not be fundamental at all. Stay with this for a moment, because it deserves attention. You are lying in the dark, listening to these words, and you are experiencing time. You feel the present moment as a distinct, vivid reality, surrounded by the remembered past and the anticipated future. The passage of time is the most immediate, undeniable feature of your conscious experience. It is more certain than anything you could verify with a measuring instrument. Whatever quantum gravity says, you are in time. You feel it. And yet the equations say, at the most fundamental level, there may be no time. How do we reconcile these two things? How does the timeless wave function of the universe give rise to the vivid, undeniable experience of temporal flow? This is not a cosmological question alone. It is also a question in physics, in philosophy of mind, and in the philosophy of science. And the answer, or rather the current best approximation to an answer, involves a concept called decoherence. Decoherence is the process by which quantum superpositions effectively collapse into classical definite states through interaction with the environment. A particle in a quantum superposition of two positions does not stay in that superposition forever. It interacts with air molecules, photons, surrounding particles, and through those interactions, the phase relationships between its quantum states become scrambled. The superposition does not literally disappear, but it becomes, for all practical purposes, a classical definite state. The quantum information leaks into the environment, spread across so many degrees of freedom that it is effectively inaccessible. In the cosmological context, decoherence is what converts the quantum superposition of early universe states into the classical definite space-time of our experience. The early universe was a quantum system. As it expanded and grew more complex, different parts of it interacted with each other, and through those interactions, certain histories became preferred, the ones consistent with smooth expanding space, with temperature fluctuations at the right level, with the arrow of time pointing in the direction of increasing entropy. The classical universe we inhabit is, in this view, not the fundamental reality, but a preferred classical branch, a consistent history that has become stable through decoherence. The arrow of time, the fact that time seems to flow in one direction, from past to future, from order to disorder, emerges in this framework from the low entropy initial conditions of the universe. The Big Bang started the universe in an extraordinarily ordered low entropy state. Everything since, every chemical reaction, every biological process, every burning candle and cooling cup of tea is an expression of that initial order gradually dispersing. Time's arrow is an entropic arrow, pointing always in the direction of increasing disorder. And this gives us a different perspective on the before question. The Big Bang was not just the beginning of matter and space. It was the beginning of the entropic gradient that defines time's direction. Whatever came before, if the word applies at all, existed either in a state of even lower entropy or in a state where entropy had no directional gradient, where time's arrow had no direction. Either possibility is extraordinary. The first possibility, a pre-existing state of even lower entropy, is exactly the problem that Penrose's conformal cyclic cosmology is trying to solve. Penrose has calculated with characteristic precision that the initial entropy of our universe was extraordinarily, almost incomprehensibly low. He estimates that out of all the possible ways a universe could have started, one like ours would occur only about 1 part in 10 to the 10 to the 123rd power, a number so large it cannot be meaningfully compared to anything in ordinary experience. It is not just improbable. It is improbability of an order so extreme that it suggests our universe's beginning was not random at all, but constrained by some deep physical principle we do not yet understand. Penrose's cyclic cosmology addresses this by arguing that the low entropy beginning of each new aeon is produced naturally by the conformal structure of the dying previous ion. The entropy that seems so outrageously low at the start of each ion is not the result of a lucky fluctuation. It is the result of a geometric mechanism that resets the entropy at each transition. Whether this mechanism actually works, physically and not just mathematically, is one of the deepest questions CCC must answer. The second possibility, a pre-bang state where entropy has no directional gradient, connects to a proposal that is perhaps the most philosophically radical of all. The idea that time, before the Big Bang, had no preferred direction. That the before state was symmetric in time. That it did not have a past and a future in any meaningful sense. That what we call the beginning was actually a symmetric point from which time emerged in both directions simultaneously. This idea has been pursued by physicists Latham Boyle, Kieran Finn, and Neil Turok at the Perimeter Institute. In their 2018 paper, they proposed a model called the CPT symmetric universe, in which our universe has a mirror image, an anti-universe that extends backward from the Big Bang in the opposite direction of time, and which is related to our universe by the combined symmetry of charge conjugation, parity reflection, and time reversal. In their picture, the Big Bang is not a beginning, but a symmetric midpoint, a reflection point from which two universes unfold in opposite temporal directions. This is mathematically elegant and physically motivated. CPT symmetry is one of the deepest symmetries in particle physics. The standard model of particle physics is believed to be exactly CPT symmetric. Boyle and Turok's model extends this symmetry to the cosmos itself, with striking results. Their model predicts that dark matter could be explained by a particular kind of neutrino, a right-handed neutrino that does not interact via the weak force, which is a specific, testable, falsifiable prediction. Some researchers find this economy compelling. The model accounts for several separate observed features of the universe using a single symmetry principle without arbitrary free parameters. Others are skeptical. The anti-universe is, by construction, causally disconnected from our own. No signal can pass from one side of the Big Bang to the other, because the Big Bang singularity separates them. The anti-universe is, in a very real sense, unobservable. And a model that postulates an entire universe that is, in principle, unobservable, raises the question of whether it is science at all, or beautiful mathematics. This is a recurring tension in quantum cosmology. Many of the most mathematically compelling proposals about what came before the Big Bang posit things that are, by construction, observationally inaccessible. The prior universe in a loop quantum bounce would, in most versions of the theory, be completely scrambled by the bounce, its information destroyed, its structure overwritten. The anti-universe of CPT symmetry is separated from us by a singularity. The other bubble universes in eternal inflation are beyond our observable horizon, in some models infinitely far beyond. Penrose's previous aeon was conformally rescaled beyond any direct detection. If the scientific method requires testable predictions, and if these proposals make predictions only about our observable universe, and not about the prior states they postulate, then how do we evaluate them scientifically? This is not a rhetorical question. It is one of the most active methodological debates in contemporary cosmology. Some physicists argue that a theory can be scientific, even if some of its implications are unobservable, as long as it makes other testable predictions. The loop quantum bounce makes predictions about the CMB power spectrum. Eternal inflation makes predictions about the statistical properties of the CMB and possibly about the distribution of physical constants. CCC makes predictions about temperature patterns in the CMB. These are genuine predictions that can be tested by current and future observations, even if the prior states they imply are inaccessible. Others argue that this is too generous, that if a theory's most important postulate, a prior universe, a prior aeon, a tunneling from nothing, is unobservable, then the theory is not well constrained by data and can accommodate almost any observational result. A theory that can accommodate anything predicts nothing. This methodological tension does not have a clean resolution. It is, in part, a reflection of the fact that we are operating at the limits of what science, as it has been practiced for the past 4 centuries, can reach. Now we turn to the specific quantum mechanical proposal that goes deepest into the before question, the one that asks not what existed before the Big Bang, but whether anything needed to. This is the proposal associated with Alexander Vilenkin's quantum tunneling from nothing, which we introduced earlier and now examine in much more detail. Vilenkin's proposal, first published in 1982 in Physics Letters B, is rooted in an analogy with a familiar phenomenon in quantum mechanics: tunneling. A particle confined in a potential well can escape by tunneling through the barrier, even if it does not have enough classical energy to climb over it. The probability of tunneling depends on the height and width of the barrier. The thicker and taller the barrier, the less probable the tunneling. But for any finite barrier, there is a non-zero probability of tunneling occurring. Vilenkin proposed that the universe itself could tunnel into existence from a state of nothing, a state with no space, no time, no matter, no energy. The barrier in this analogy is the constraints imposed by the quantum state of nothing. The tunneling is the spontaneous appearance of a universe with a small but non-zero size, which then undergoes inflation and grows into the vast cosmos we observe. The mathematical formulation of this proposal uses the Wheeler-DeWitt equation, the timeless quantum equation for the universe. Vilenkin imposes a specific boundary condition. The wave function of the universe should include only outgoing waves, waves that represent universes expanding away from nothing, with no contribution from waves traveling back toward nothing. This is analogous to the Sommerfeld radiation condition in classical wave physics, which specifies that waves must be outgoing at infinity. It is a natural mathematical choice, but it is a choice. It is not forced by the equations alone. With this boundary condition, the wave function of the universe assigns a probability amplitude to different initial configurations of the cosmos. The most probable configurations are those with a small but finite size, universes that nucleate from nothing with just enough energy to begin inflating. From there, inflation takes over, expanding the universe by an enormous factor and filling it with the matter and radiation we observe. Here's where the proposal becomes both compelling and troubling. Vilenkin's nothing is not quite nothing. It is a state with no space and no time, yes. But it is a state in which quantum mechanics applies. It is a state in which there is a wave function, a Hilbert space of possible states, a mathematical framework for computing transition probabilities. This framework is not nothing. It is something abstract, something without physical extent or duration, but something with mathematical structure that determines what can and cannot emerge from it. Critics of Vilenkin's proposal, and there are serious ones, argue that this is circular. If the laws of quantum mechanics are in place before the universe exists, then the laws of physics exist before the universe exists. But where did the laws come from? The proposal replaces the question, why is there something rather than nothing, with, why are there these specific laws of quantum mechanics rather than no laws? It does not eliminate the mystery of origins, it relocates it. Vilenkin's response to this criticism is that the laws of physics are not physical entities. They do not require space-time to exist. They are mathematical truths, and mathematical truths do not need a physical substrate to be true. The sum of 2 and 2 is 4, whether or not there is a universe to contain mathematicians to discover it. If physical laws are mathematical truths of a certain kind, then they do not come into existence with the universe. They simply are, timelessly and necessarily. And the universe is the physical realization of one such mathematical truth. This response connects to a broader philosophical position associated with physicist Max Tegmark, who argues that every mathematically consistent structure exists as a physical reality. In Tegmark's mathematical multiverse, our universe is not special. It is simply one of infinitely many mathematical structures that physically exist, each with its own laws and constants. The laws of our universe are not chosen or fine-tuned. They are simply the particular mathematical structure we find ourselves in, selected by the anthropic requirement that complex observers can exist. This is a position at the very edge of what physicists are comfortable calling physics. Some regard it as a profound insight. Others regard it as unfalsifiable metaphysics dressed in mathematical clothing. The debate is genuine, unresolved, and likely to remain so for a very long time. We are now deep enough in our descent to examine what may be the most technically sophisticated and mathematically developed approach to the before question, and one of the youngest. This is the approach known as causal dynamical triangulations, or CDT, developed primarily by physicists Jan Ambjorn at the Niels Bohr Institute in Copenhagen and Renate Loll at Radboud University in the Netherlands, beginning in the late 1990s. CDT is a non-perturbative approach to quantum gravity, meaning it attempts to compute the path integral of quantum gravity directly, without making any small parameter approximations. In CDT, space-time is approximated as built from tiny four-dimensional simplices, the four-dimensional analog of triangles, that are assembled together according to specific causal rules. The causal rules are crucial. They enforce that the space-time built from these simplices has a consistent causal structure with a well-defined notion of before and after at each point. This is in contrast to some earlier approaches to quantum gravity that allowed space-time to have a causal baby universe structures, connections between different points that violate the usual causal ordering. By computer simulation, CDT generates ensembles of these triangulated spacetimes and computes averages over them. The quantum gravitational path integral made numerically concrete. And what these simulations find is striking. At large scales, the simulated spacetimes look like our universe, four-dimensional, smoothly expanding, with the geometry described approximately by general relativity. At the Planck scale, however, the simulated spacetime has a very different character. It has an effective dimensionality of 2, not 4. Spacetime, in CDT simulations, appears to be effectively two-dimensional at the smallest scales, growing to its familiar four-dimensional character at larger scales. This dimensional reduction at the Planck scale, the emergence of an effectively lower dimensional structure at the smallest scales of spacetime, is a prediction also made by several other approaches to quantum gravity, including loop quantum gravity and certain string-inspired models. If this reduction is real, it has profound implications for the before question. In a two-dimensional spacetime, there are no independent space dimensions. Space and time collapse into a single, unified, lower-dimensional structure. The familiar separation of space and time, the geometry that supports our ordinary notions of before and after, simply does not exist at this scale. In CDT simulations, the early universe, the before, is not a prior history, but a different phase of the same spacetime. It is a regime where the geometry is dominated by quantum fluctuations, where the effective dimensionality is reduced, and where the classical notions of space and time do not apply. There is no sharp boundary, no wall, no singular moment. There is a gradual transition from the quantum-dominated low-dimensional regime at the smallest scales to the classical four-dimensional geometry we experience at large scales. If CDT is right, and it is a significant if, since CDT is a computational framework, not a complete theory, and its simulations involve approximations and choices that may or may not be physically correct. Then, the before of the Big Bang is a regime of effectively two-dimensional quantum geometry, from which four-dimensional space-time emerged as the universe expanded and cooled below the Planck energy. The question, what was before, becomes, what was quantum geometry like in the two-dimensional regime? Which is a question that CDT is, in principle, equipped to address and is actively investigating. Anaphora captures the rhythm of these approaches. They are different routes toward the same precipice. Some come from the mathematics of quantum mechanics. Some come from the geometry of space-time. Some come from the thermodynamics of entropy and the arrow of time. All of them terminate at the same place, the Planck scale, the boundary beyond which our classical and even our quantum mechanical concepts may simply not apply. This is worth pausing to appreciate. The sheer range of approaches, Hartley-Hawking no boundary, loop quantum bounce, conformal cyclic cosmology, CPT symmetric universe, quantum tunneling from nothing, causal dynamical triangulations, reflects not a failure of physics, but a success of imagination. Physics has generated multiple internally consistent, mathematically serious proposals for what came before the Big Bang. The problem is not a lack of ideas. The problem is a lack of observational leverage, a lack of data that can discriminate between these proposals. And this lack of leverage is, to a significant extent, permanent, not temporary, not something that will be resolved by the next generation of telescopes or the next particle accelerator. Permanent in the sense that the physics of the Planck regime, the epoch before inflation, before the CMB, before any known physical process, left a distinguishable imprint, that physics may simply be erased from any observable record. Inflation is, in this sense, both our greatest tool for understanding the early universe and the greatest obstacle to understanding what came before. Inflation expanded the universe by an enormous factor, smoothing out and diluting virtually everything that existed before it. Whatever preceded inflation, whatever quantum state, whatever prior universe, whatever bounce or tunneling event, was almost completely overwritten by the inflationary expansion. The CMB carries the imprint of what happened during and after inflation. But the pre-inflationary epoch is behind an information horizon as real and perhaps more impenetrable than the CMB itself. Some researchers think this is genuinely the end of the road, that the pre-inflationary universe is permanently inaccessible, and that asking what came before is asking a question that science, by its nature, cannot answer. Jean-Luc Lehners at the Max Planck Institute for Gravitational Physics in Potsdam, Germany, has expressed this with characteristic directness. I think it's completely preposterous that in the year 2025 we should understand the beginning of the universe. This is not defeatism, it is scientific honesty. Lehners is not saying the question is meaningless. He is saying it is genuinely, profoundly hard, and that intellectual humility requires acknowledging how far we still have to go. Why not in the year 2225, he asks. And this too is a form of wisdom, a recognition that the universe is not obligated to arrange its most profound mysteries at a scale accessible to our current instruments. But other researchers are less pessimistic about the prospects for observational traction on the before question. They point to gravitational waves, ripples in space-time produced by cataclysmic events, as a potential window into the pre-CMB universe. Unlike photons, gravitational waves interact extremely weakly with matter and can propagate freely through even the opaque plasmas of the early universe. primordial gravitational waves, waves produced during or before inflation, would, if detected, carry information about the energy scale of inflation, the details of the inflationary potential, and potentially even about pre-inflationary physics. The BICEP and Keck array experiments at the South Pole Station in Antarctica have been searching for the signature of primordial gravitational waves in the polarization of the CMB. The signal they are looking for, called B-mode polarization, is produced when gravitational waves stretch and squeeze space in the early universe, leaving a distinctive swirling pattern in the polarization of the CMB photons that were scattered at the surface of last scattering. So far, primordial gravitational waves have not been detected. The experiments have placed upper limits on the ratio of gravitational wave power to density fluctuation power, a quantity called the tensor-to-scalar ratio, but have not seen a positive signal. Future experiments, including Lightbird, a planned Japanese Space Agency satellite designed to measure CMB polarization with unprecedented precision, may push the detection sensitivity down to where some inflationary models predict a signal should be visible. If primordial gravitational waves are detected, and if their properties match the predictions of a specific inflationary model, that would be a profound confirmation of our understanding of the very early universe. It would not directly confirm anything about what came before inflation, but it would constrain the energy scale at which inflation occurred, which in turn constrains what could have preceded it. There is also the possibility, speculative but not dismissed, that other types of primordial signals could carry information about pre-inflationary physics. Primordial black holes, if they formed in the early universe, would contribute to the gravitational wave background. Topological defects, cosmic strings, domain walls, monopoles, if produced in a phase transition before or during inflation, might leave detectable signatures. And the JWST and future telescopes continue to probe the earliest galaxies, testing our models of cosmic structure formation and potentially finding anomalies that force revisions to our understanding of the early universe. The anomalies question is, in fact, one of the most actively debated in contemporary cosmology. Several features of the CMB have, at various times, been claimed as departures from the predictions of standard inflation. An anomalously low quadrupole moment, an asymmetry in the power of temperature fluctuations between the two hemispheres of the sky, a cold spot in the southern hemisphere. Each of these anomalies could, in principle, be a signature of pre-inflationary physics, a faint imprint of the quantum geometry that preceded inflation, preserved despite the enormous dilution that inflation caused. Or each could be a statistical fluctuation, a random pattern that appears significant only because we have looked hard enough that chance alone produces something noteworthy. Distinguishing between a genuine signal and a statistical artifact in a dataset with only one universe to observe is extraordinarily difficult. We cannot run the Big Bang again with different initial conditions to build up statistics. We have one sky, one set of CMB fluctuations, one realization of cosmic structure. And with one realization, the statistical significance of any claimed anomaly is always, fundamentally, limited. This is the deepest epistemic challenge in cosmology. We are attempting to understand the unique, once occurring unrepeatable origin of the universe, using methods designed for repeatable experiments. The scientific method, in its most stringent form, requires repeatability, the ability to perform the same experiment multiple times under controlled conditions and compare the results. The Big Bang is not repeatable. The universe is not a laboratory sample. And the question of what came before the Big Bang is, perhaps more than any other question in science, resistant to the methodological tools that have made science so extraordinarily successful in every other domain. This does not make the question unscientific. It makes it science at its hardest. Science pushed to the boundary of what reason, mathematics, and observation can reach. And it means that the answers we arrive at when we arrive at them will likely be stranger and more surprising than anything we currently imagine. Now we descend to the layer where the strangeness is most acute, the layer of quantum vacuum and the meaning of nothing. Because one of the most important and least understood features of the before question is the question of what it means for there to be nothing at all. In quantum mechanics, the vacuum, empty space from which all particles have been removed, is not nothing. It is a quantum state, the lowest energy state of a quantum field. And this quantum vacuum is extraordinarily active. Virtual particles, particle-antiparticle pairs, continuously spring into existence and annihilate each other, too short-lived to be directly observed, but leaving measurable traces in the physical world. The Casimir effect, first predicted by Hendrik Casimir in 1948, is a direct consequence of quantum vacuum fluctuations. Two uncharged conducting plates placed very close together in a vacuum experience an attractive force because the vacuum between them has fewer possible modes of fluctuation than the vacuum outside, creating a pressure imbalance. This effect has been measured in laboratory experiments with high precision. The Lamb shift, discovered by Willis Lamb and Robert Rutherford in 1947, is another consequence of vacuum fluctuations. The energy levels of the hydrogen atom are shifted very slightly from their predicted values by the interaction of the electron with the fluctuating electromagnetic vacuum. The Lamb shift is measured to extraordinary precision. It is one of the most precisely confirmed predictions in all of physics. These effects confirm that the quantum vacuum is not nothing. It is a seething dynamic state of quantum fields, a landscape of virtual activity that has real, measurable consequences. And this is enormously important for the before question, because it means that even if the universe emerged from nothing, the nothing from which it emerged was not the philosophical nothing of complete absence. It was at minimum a quantum vacuum, a state with specific mathematical properties, governed by specific laws. Here's where that picture's apparent simplicity breaks down. The laws that govern the quantum vacuum of our universe, quantum field theory, gauge symmetries, the specific particle content of the Standard Model, are features of our universe. They are not universal features of every possible quantum vacuum. Different universes with different physical laws would have different vacua with different properties. The quantum vacuum of our universe is what it is because our universe has the laws it has. You cannot invoke the quantum vacuum as an explanation for the origin of the universe without first explaining why the quantum vacuum has the properties it does, which means explaining why the laws of physics are what they are. This is sometimes called the laws of physics problem, and it is, in a certain sense, more fundamental than the what came before problem. Even if we fully understood the quantum cosmological mechanism by which our universe began, even if Vilenkin's tunneling proposal or Hartley-Hawking's no-boundary proposal were rigorously confirmed, we would still be left asking, why these laws? Why quantum mechanics? Why general relativity? Why the specific values of the fundamental constants, the fine structure constant, the cosmological constant, the masses of the elementary particles that make our universe capable of harboring stars and planets and life? The question of why the constants have the values they do is called the fine-tuning problem, and it is one of the most debated topics in both physics and philosophy. The constants of nature appear in many cases to be extraordinarily finely tuned for the existence of complex structures. Change the fine structure constant by a few %, and the chemistry of carbon, and therefore all biochemistry, becomes impossible. Change the cosmological constant by a tiny fraction from its observed value, and the universe either collapses immediately or expands so rapidly that no structures ever form. Change the ratio of the electromagnetic force to the gravitational force, and stars either cannot ignite or cannot maintain stable burning. These coincidences, and there are many of them, suggest either that the constants are not coincidences at all, but are determined by some deep physical principle we have not yet discovered, or that they are the result of a selection effect operating over a vast landscape of possible universes, each with different constants. And we find ourselves in one where complex life is possible simply because we could not exist in any other. This second explanation is the anthropic principle, and it is invoked most naturally in the context of eternal inflation, where the different bubble universes spawned by the inflationary process might each have different physical constants, sampling the landscape of string theory, which is thought to allow an astronomically large number of possible vacuum states, perhaps 10 to the 500 or more. Some researchers find the anthropic explanation deeply satisfying. It replaces a mystery about coincidence with an observation selection effect, the same logic by which we explain why we live on an Earth with liquid water, rather than one of the many planets without it. Others find it intellectually empty. It predicts nothing, explains nothing, and simply relabels the mystery. The debate is unresolved, and, once again, may be permanently unresolvable, because the other bubble universes in eternal inflation are observationally inaccessible. We have now traversed a very large amount of territory. From the solid ground of observational cosmology, the CMB, the expansion of the universe, the measured age of 13.8 billion years, through the physics of inflation and the Border-Guth-Vilenkin theorem, through the major families of before proposals, no boundary, loop quantum bounce, conformal cyclic cosmology, CPT symmetric universe, quantum tunneling from nothing, through the problem of time in quantum gravity and the Wheeler-DeWitt equation, through causal dynamical triangulations and the dimensional reduction of spacetime, through the quantum vacuum and the fine-tuning problem and the anthropic principle. Each layer has added complexity. Each layer has revealed that the layer beneath is stranger than the one above. And each layer has revealed a new version of the same fundamental tension. The universe, as we observe it, with its specific laws and constants and history, demands an explanation. The explanations we have are beautiful and mathematically serious, but unconfirmed, and, in many cases, permanently unconfirmable. And the explanations we would need to be fully satisfied, an account of why the laws of physics exist, why they have the specific form they do, and why there is something rather than nothing, may lie beyond the reach of any science we can currently imagine. There is one more domain of strangeness that we must examine before the intellectual climax of this exploration. It is the domain of string theory and the landscape. Because string theory, the most ambitious attempt in the history of physics to unify all forces and particles into a single framework, has something remarkable and troubling to say about the before question. And what it says changes the nature of the question in ways that are still being absorbed. String theory proposes that the fundamental constituents of reality are not point particles, but tiny one-dimensional objects, strings, whose different vibrational modes correspond to different particles. A string vibrating in one mode is an electron. Vibrating in another, it is a quark. Vibrating in another, it is a graviton, the hypothetical carrier of the gravitational force. String theory naturally incorporates gravity alongside the other forces, something that ordinary quantum field theory cannot do. This is its great appeal. It is, potentially, a theory of everything. But string theory requires extra dimensions of space, typically 6 or 7 beyond the 3 we experience, that are compactified or curled up at scales too small to observe. And the way these extra dimensions are compactified determines the effective laws of physics in the 4-dimensional universe we inhabit. The particle content, the force strengths, the values of the fundamental constants. Different compactifications give different effective laws. And here is the problem, and the source of the landscape. The number of consistent compactifications in string theory is not small. It is not 100 or 1,000,000, or even 1,000,000,000,000. Estimates suggest that the number of consistent string theory vacua, different ways of compactifying the extra dimensions, each giving a different set of effective physical laws, may be of order 10 to the 500. Some estimates go higher. This number is so incomprehensibly large that it essentially means string theory, as currently formulated, does not predict a unique set of physical laws. It predicts a vast landscape of possible laws, with no obvious principle for selecting among them. In eternal inflation, this landscape may become physical. Different bubble universes in the eternally inflating multiverse may correspond to different points in the string theory landscape, different compactifications, different effective laws, different constants of nature. Our universe would be one bubble among an essentially infinite number, with our specific laws and constants selected, not by any fundamental principle, but by the anthropic requirement that they allow complex observers to exist. This is, if true, a radical restructuring of what science is trying to do. The goal of physics, at least as it was traditionally conceived, was to find the unique set of laws that correctly describes reality and to understand why those laws and not some others. The landscape picture, if correct, says there is no unique set of laws, no deep reason why our constants are what they are, no fundamental principle waiting to be discovered. There is only the vast proliferation of possibilities and the accident of which one we happen to inhabit. Many physicists find this conclusion deeply unsatisfying, almost to the point of being a reductio ad absurdum of the assumptions that led to it. If string theory leads to the landscape, and the landscape leads to the multiverse, and the multiverse leads to the anthropic principle as the only available explanation for our constants, then string theory may have failed. Not by being wrong, but by being too rich, too capable of accommodating anything, and therefore capable of predicting nothing in particular. Others, including some of the architects of eternal inflation, accept the landscape and multiverse as the most honest available picture of reality. Vast, humbling, and scientifically tractable, if not in its full scope, at least in its predictions for our observable corner. The before question in the string landscape picture takes a different form. Before our Big Bang, there was the eternally inflating space-time. Before that, before the particular bubble nucleation event that produced our inflationary episode, there were other bubble nucleations, other universes with other laws. Before the beginning of eternal inflation, there was the beginning of the inflationary space-time itself, which, by the Border-Guth-Vilenkin theorem, cannot be pushed infinitely far into the past. Before that, before the very beginning of the string landscape's physical realization, there was, perhaps, the timeless mathematical structure of string theory itself, existing in the same abstract sense as any other mathematical truth. And before the mathematical truth, nothing, or everything, or the question itself ceases to apply. We have descended as far as current physics can take us. Take a moment to look back at the path. We began at the clock on the wall. We traced the universe back through 13.8 billion years of observable history, through the CMB wall at 380,000 years, through inflation at 10 to the negative 36 seconds to the Planck wall at 10 to the negative 43 seconds. We examined the no-boundary proposal, loop quantum cosmology, conformal cyclic cosmology, the CPT symmetric universe, quantum tunneling from nothing, causal dynamical triangulations, and the string landscape. Each layer revealed that the one beneath it was stranger. Each answer dissolved into a deeper question. Now we turn to the place where all of these threads pull together, where the individual proposals stop being proposals and start being symptoms of something larger. Where the question, what was there before the Big Bang, reveals itself to be not one question, but several, nested inside each other like a set of matryoshka dolls, each one smaller and harder to open than the last. And where physics, pressed to its absolute limit, opens onto something that is no longer quite physics, but something that physics, by its very inadequacy, points toward. This is the intellectual core of what we are exploring, the place where the map runs out and the territory becomes its own kind of answer. Begin by standing very still. Picture yourself at the edge of an ocean at night. The water is black. The sky is black. You cannot tell where the ocean ends and the sky begins. You know, intellectually, that there is a horizon, a line where the curvature of the earth carries the water beyond your sight. But you cannot see it. You can only feel it, the way you feel the edge of sleep, the point at which awareness begins to dissolve, not into nothing, but into something you cannot describe from the inside. The Planck scale is that horizon for physics. We know it is there. We know that beyond it, the familiar geometry of space-time gives way to something we cannot describe from the inside of our current theories. And everything we have examined, every proposal, every mathematical framework, every bold speculation, is a way of trying to describe what lies beyond the horizon, using tools built on this side of it. Something here deserves particular attention because it reframes everything that has come before. Every single proposal for what came before the Big Bang, without exception, makes one of two fundamental assumptions. Either it assumes that time, in some form, existed before the Big Bang, and therefore that before is a meaningful temporal concept, as in loop quantum cosmology, conformal cyclic cosmology, the CPT symmetric universe, eternal inflation. Or it assumes that time itself emerged at or near the Big Bang, and therefore that before is not a temporal concept, but a geometric or quantum mechanical one, as in the Hartley-Hawking no-boundary proposal, the Wheeler-DeWitt timeless universe, the dimensional reduction of causal dynamical triangulations. These two assumptions are not merely different answers to the same question. They are different versions of the question. They are asking about fundamentally different things, and they cannot both be right. But here is what is extraordinary. They might both be wrong in the same way. Consider the possibility, genuinely considered by a small number of theorists, but not yet worked out in full detail, that neither time before the bang nor no time before the bang captures what is actually going on. Consider the possibility that time, as a concept, is not binary, that it does not simply exist or not exist. Consider the possibility that time is a continuous variable that emerges gradually from a more fundamental structure, the way that temperature emerges from the collective motion of molecules. Temperature is not a property of a single molecule. It is a property of an ensemble, a statistical description of how energy is distributed across many degrees of freedom. Below a certain scale, the concept of temperature ceases to apply. You cannot ask about the temperature of a single photon, only about the temperature of a gas of photons. What if time is like temperature? What if time is a concept that applies to the universe only above a certain scale, the Planck scale? And below that scale, the concept simply does not apply, not because time stops, but because the degrees of freedom from which time emerges as a statistical property have not yet organized themselves into a temporal structure. This idea, that time is emergent from a more fundamental, timeless structure, is explored in the framework of quantum information and holography. In the holographic principle, developed from insights by Leonard Susskind at Stanford University and Gerard 't Hooft at Utrecht University in the 1990s, the information content of a region of space is encoded on its boundary, much as a three-dimensional hologram is encoded on a two-dimensional surface. In the most developed version of holography, the ADS/CFT correspondence, discovered by Juan Maldacena at Harvard University in 1997, a theory of gravity in a space with a certain geometry, anti-de Sitter space, is exactly equivalent to a quantum field theory without gravity on the boundary of that space. Gravity in the bulk, including the geometry of space-time, emerges from the quantum entanglement structure of the boundary theory. In this framework, space-time, including time, is not fundamental. It is a derived structure, emerging from patterns of quantum entanglement in a theory that has no space-time to begin with. The geometry of the interior is encoded in the entanglement structure of the boundary. Change the entanglement, and the geometry changes. Disconnect the entanglement, and the interior space-time ceases to exist as a geometric structure. If space-time, including time, emerges from quantum entanglement in this way, then asking what came before the Big Bang is asking about the temporal structure of a regime where space-time has not yet emerged from its quantum substrate. It is asking about the geometry of a space that does not yet have a geometry. The question is not malformed in the sense of being logically incoherent. It is malformed in the sense of applying a concept to a regime where the concept has not yet crystallized out of the underlying physics. This is the deepest version of the category error answer. And it is different from the Hartley-Hawking version, which still uses geometric concepts, the smooth Euclidean geometry, to describe the beginning. The holographic/emergent spacetime version says, at the deepest level, there is no geometry, not even the Euclidean kind. There is only entanglement. There is only information. And spacetime, with its directions and its distances, and its causal structure and its arrows of time, is a large-scale approximation to the quantum information structure of a universe that is, at its most fundamental level, not made of space or time at all. Now we must ask, what is that fundamental level made of? This is the question at which physics currently has no answer. Not an incomplete answer, not a provisional answer, no answer. The fundamental constituents of the quantum information structure from which spacetime might emerge, if the holographic/emergent picture is correct, are not known. They go by various names in various frameworks: spin networks in loop quantum gravity, qubits of spacetime in some quantum information approaches, the fundamental degrees of freedom of the boundary, CFT in ADS/CFT. But none of these names corresponds to a fully worked out physical theory that correctly describes our universe. We are not even certain that space-time is emergent from something more fundamental, in the way that holography suggests. A DS/CFT is the most precise realization of holography we have, but it describes a universe with a negative cosmological constant, an anti-de Sitter space, whereas our universe has a positive cosmological constant. Extending holography to de Sitter space, the geometry of our actual universe, is one of the most active and unresolved problems in theoretical physics. Some researchers believe it can be done, that de Sitter holography will eventually be understood, as well as anti-de Sitter holography. Others believe that de Sitter space is fundamentally different, that holography may not apply to it in the same way or may not apply at all. And here is where we must make a genuine admission of irreducible uncertainty. We do not know whether the holographic/emergent spacetime picture is correct. We do not know whether ADS/CFT extends to de Sitter space. We do not know whether time is emergent from a more fundamental timeless structure, or whether it is fundamental and simply had a beginning. We do not know whether the Planck scale marks a regime of different physics or the absolute limit of any physics at all. These are not questions that are merely awaiting better experiments. They are questions whose resolution may require conceptual revolutions of the kind that occurred when Newton gave way to Einstein, or when classical mechanics gave way to quantum mechanics. And those revolutions cannot be scheduled. What can be said with confidence is this: the before question has forced physics into a domain where its most basic concepts, space, time, causation, identity, existence, are themselves in question. The question has not been answered. It has been deepened. Every layer of understanding we have added has not brought us closer to a simple resolution, but has revealed a more complex and more subtle terrain beneath. And this deepening is not a failure. It is the mark of a genuinely profound question. Only questions that touch the most fundamental aspects of reality become deeper as they are explored. Shallow questions become exhausted. Deep questions become canyons. Now the rhetorical questions must come, because this is the place where language catches up with mathematics and the two face each other honestly. What does it mean for something to begin? What does it mean for something to exist before it begins? Can there be a cause with no prior time in which to operate? Can there be a law with no universe to enforce it? Can there be a mathematical structure with no mind to contemplate it? Can there be something, anything that requires no explanation, that simply is, without reason or origin? Or is everything, every state, every law, every mathematical truth, the product of something prior, an infinite regress with no first term? If there is no first term, if the chain of causation extends infinitely into the past, then the universe has always existed in some form, and the before of our particular Big Bang points to a prior state that itself points to a prior state without terminus. This is philosophically uncomfortable, but not logically impossible. Infinite regresses are legitimate mathematical structures. The integers extend infinitely in both directions without paradox. But if there is a first term, if there is something that had no cause, no prior state, no explanation in terms of anything else, then that first term must be, in some sense, necessary. It must be the kind of thing that could not have been otherwise. It must contain within itself the reason for its own existence. What could that possibly be? Philosophers have proposed several answers. Some say it must be a necessary being, something whose non-existence is logically impossible, something that exists in all possible worlds. Some say it must be pure existence itself, existence without any particular form, the ground of being that underlies all specific existence. Some say it must be the mathematical structure of physical law, the abstract truth that 2 + 2 = 4, extended to the full mathematical structure of a universe. Some say it must be consciousness, that consciousness is the only thing we know directly, from the inside, and that a universe without prior consciousness is stranger than one in which consciousness was the ground. None of these answers is scientifically testable. They are all, in the strictest sense, metaphysics, reasoning about what must be true beyond the range of any possible observation. And yet, they are not arbitrary. They are constrained by logic, by consistency, by the requirement that they cohere with everything physics has told us about the structure of reality, and they converge on a single, extraordinary insight. The before question cannot be answered by physics alone. Not because physics is incomplete, though it is. Not because we lack the right theory of quantum gravity, though we do. But because the question, at its deepest level, is asking about the conditions under which physics itself is possible. It is asking about the origin of the laws, the origin of the mathematical structure, the origin of the possibility of causation and existence. And those conditions cannot be explained by physics, because physics is built on them. To explain the foundations of physics using physics is like trying to lift yourself by your own bootstraps. The thing you are trying to lift is the very thing doing the lifting. This is not mysticism. It is logical. And it is one of the most important things that physics has discovered. Not a positive discovery, not a new particle or a new force, but a boundary. A boundary that is as real and as precisely located as any physical measurement. The boundary beyond which physics, by its own internal logic, cannot reach. Some researchers respond to this boundary with what might be called noble resignation. The acknowledgement that there are questions we cannot answer, that the universe is not obligated to be fully comprehensible to the minds that arise within it, and that this incomprehensibility is itself a kind of wonder. Others respond with continued pressing, insisting that the boundary is provisional, that future theories will push it further, that what seems inexplicable today will be obvious tomorrow. History offers examples on both sides, questions that seemed permanently beyond reach that were later resolved, and questions that were thought to be on the verge of resolution that turned out to open into even deeper mysteries. What distinguishes the before the Big Bang question is that it combines both features. The specific scientific questions, what the quantum state of the early universe was, whether it underwent a bounce, whether there was a prior aeon, are in principle scientifically tractable, even if currently unresolved. The deeper philosophical questions, why there are laws at all, why there is something rather than nothing, what it means to exist without a prior cause, are not scientifically tractable in the same way and may never be. They are the permanent horizon, receding as we approach it, always present. Now we must pivot to the place where this matters most, where the abstract becomes concrete, where the philosophical becomes personal. Because the question of what came before the Big Bang is not merely an academic puzzle. It is, when understood fully, a question about the nature of existence itself, about what it means for anything to be here at all. And that is a question that touches every conscious being who has ever lived on this small, improbable planet. Pause here, because this is the existential core. You are here. You are made of atoms that were forged in the cores of stars, scattered across the galaxy when those stars exploded, gathered again by gravity into a new solar system, incorporated into the chemistry of a planet, and organized over 4 billion years of biological evolution into a system complex enough to ask why it exists. You are the universe asking itself about its own origin. You are matter looking back through time at the moment from which it came, using eyes and brains and language that arose by processes that the universe set in motion 13.8 billion years ago. This is not rhetorical decoration. It is a physical fact. The carbon in your cells was fused in a stellar core. The iron in your blood was produced in a supernova. The hydrogen in your water is as old as the universe itself, forged in the first 3 minutes before a single star had formed. You carry the history of the cosmos in your body, literally at the atomic level. And the consciousness that animates that body, the awareness that is reading these words, experiencing this moment, asking these questions, is the universe's most elaborate known mechanism for examining itself. When you ask, what was before the Big Bang? You are not asking about something remote and irrelevant. You are asking about your own origin, about the first cause of every atom in your body, every pattern of electrochemical activity that constitutes your thoughts, every relationship and memory and hope that makes your life your own. The question reaches backward through 13.8 billion years and touches the moment from which everything you are, everything you have ever experienced, ultimately arose. And the answer, if we are honest, is we do not know. We have beautiful theories. We have mathematical frameworks of extraordinary elegance. We have brave proposals by some of the finest minds in the history of science. We have ruled out some naive answers and discovered that the true answers are far stranger than the naive ones. But we do not know. We genuinely, profoundly do not know. This admission, made honestly without apology, is itself a form of knowledge. The precise location of our ignorance is something we have worked hard to find. And knowing exactly where we do not know is a different and more honest position than not knowing that we do not know. Now consider what the various proposals, each in their own way, imply about the relationship between existence and time. The no-boundary proposal implies that time is not a precondition of existence, that the universe existed in a sense that does not require a before. This is deeply counterintuitive because every form of existence we have ever experienced has been embedded in time. We experience things beginning and ending. We experience preceding effects. We experience our own consciousness as a thread moving through moments. The idea of an existence that precedes time, or more precisely, an existence for which time is an emergent property rather than a container, requires abandoning one of the deepest assumptions built into human cognition. The loop quantum bounce implies that time is fundamental and infinite in extent, that there was always a universe of some kind, that the beginning we experience was a middle, a bounce, a transition, a transformation of what came before into what came after. This is more intuitively satisfying in a way because it preserves the familiar framework of temporal sequence. But it pushes the question of origins back indefinitely. If there was a universe before our Big Bang, what was before that universe? And before that? And before that? The bouncing universe might be eternal in both directions, but it does not explain why there is a universe at all. It only says that there always has been one. Conformal cyclic cosmology implies something stranger still, that beginning and end are not opposites, but complements, that the death of one universe is the birth condition of the next, that the universe is simultaneously eternal and locally finite, that the vast expansion into cold darkness that awaits our cosmos in the far future is not a tragedy, but a preparation. In Penrose's vision, the universe does not die. It transforms. The light of the last black holes, scattered across an infinite void, becomes the first warmth of a new creation. A creation so different from ours that nothing of ours survives it, except, perhaps, the faintest geometric echo in the first light of the next universe's morning. The tunneling from nothing implies that existence is not something that needs to be maintained or transmitted from a prior state. It implies that the universe was not caused by anything that preceded it, because there was nothing preceding it to do the causing. It implies that existence is, in some sense, its own first act, that the universe wrote itself into being through the logic of quantum mechanics, which permits transitions with no classical cause. This is philosophically the most radical option: existence without cause, beginning without antecedent. Creation ex nihilo, but not by a creator, by the logic of possibility itself. And the holographic/emergent space-time picture implies that the very framework we use to ask these questions, the framework of space and time and causation, is not fundamental, but constructed. That it is built from something deeper: quantum information, entanglement, the mathematical structure of a boundary theory. And that the question, what was before the Big Bang, is a question asked within the constructed framework about the conditions from which the framework itself emerged. It is a question, in a precise sense, that is trying to see outside its own eyes. Here is what happens when you place all of these proposals side by side and look at them simultaneously. Each one, when understood deeply, undermines the assumptions on which the naive version of the before question rests. Each one shows that one or more of the concepts embedded in the question, before, time, existence, beginning, nothing, cause, is more complicated, more contingent, more constructed than it appears. Each one reveals that the question is not simple because the answer is not known, but because the question itself is entangled with the deepest features of reality. And each one, paradoxically, makes the fact that there is something rather than nothing more mysterious, not less. The naive version of the question assumes that the existence of the universe is a puzzle whose solution will arrive in the form of a prior state, something that was there before, from which the universe came. Each sophisticated answer has shown that this assumption does not work. The prior state, whatever form it takes, still requires explanation. The nothing from which the universe tunneled was not truly nothing. The prior aeon from which our Big Bang emerged had its own origins. The timeless quantum geometry from which time emerged was itself a specific, structured mathematical object with no explanation for its own existence. What is before the Big Bang? Whatever it is, and physics has given us many beautiful guesses, it does not resolve the mystery of existence. It deepens it. The mystery deepens at each layer, not because we are failing to find the answer, but because the question is genuinely, irreducibly deep. What is deeper than the deepest layer? What is before the first before? What is outside the largest context? What is the ground of all possible mathematical structures? We cannot know, not provisionally, not temporarily, not in the sense of we will figure it out eventually. We cannot know because the act of knowing requires a knowing mind, embedded in time, using conceptual frameworks built from the very features of reality whose origins are in question. To know the origin of time, you would need to be outside of time. To know the origin of existence, you would need to be outside of existence. These are not practical limitations, but logical ones. And yet, and this is what makes the question not merely important but beautiful, the inability to answer does not make the asking futile. Every step we have taken toward the answer has taught us something real. General relativity told us that space-time is physical and can have a beginning. Quantum mechanics told us that the vacuum is not empty and that tunneling without classical cause is possible. Inflation told us that our observable universe is a bubble in a vastly larger cosmos. Loop quantum gravity told us that the singularity may not be a wall, but a bounce. Holography told us that space-time may be emergent from information. Each of these is a genuine piece of knowledge, hard-won, mathematically precise, observationally constrained where possible. The frontier of the before question is not a void. It is a landscape of partial answers, each illuminating a different aspect of the mystery, each consistent with what we know, each extending our understanding further into the dark. And the fact that no single proposal has emerged as definitively correct is not a disappointment. It is an invitation to keep thinking, keep calculating, keep observing, keep asking. This is where the intellectual climax arrives, not with an answer, but with a recognition. What if there were no prior state at all? What if the universe, not just the matter and energy and space-time, but the laws, the mathematical structure, the possibility space from which anything could emerge, arose from a state that was not a state? What if nothing is not a container out of which something emerged, but the limit approached as all constraints are removed? And what if the removal of all constraints is itself constrained by the very logic of possibility? The philosopher Gottfried Wilhelm Leibniz asked in 1714, "Why is there something rather than nothing?" It is sometimes called the fundamental question of metaphysics. And what is remarkable, what the entire history of physics and cosmology we have traced together teaches, is that science has gotten close enough to this question to appreciate, with full technical precision, why it is so hard. The question, why is there something rather than nothing, is not answered by pointing to a prior something, because then you have merely shifted the question. It is not answered by pointing to the laws of quantum mechanics, because those laws are themselves something. It is not answered by pointing to the mathematical structure of all possible universes, because mathematical structure is itself something. Every answer that has been proposed, every prior state, every quantum vacuum, every mathematical multiverse, every necessary being, is itself a something, and the question simply resurfaces. Why that something rather than nothing? The only honest answer is, we do not know. We may never know. And the inability to know may itself be telling us something important. That the question is touching a genuine boundary, a place where the categories with which we understand reality cannot reach. Not because our categories are poor instruments, but because the question is asking about the conditions for the existence of any instruments at all. This is not nihilism. The fact that the deepest question cannot be answered does not mean that nothing can be known or that the universe is meaningless. It means the opposite, that the universe is not exhausted by what we can know about it, that there is depth beyond depth, that existence is not a fact to be explained, but a mystery to be inhabited. And here is the realization that reframes everything that came before it in our exploration. Every civilization that has ever existed on this planet has looked up at the sky and asked some version of this question. Every culture that has generated a cosmological myth, Babylonian, Egyptian, Hindu, Greek, Norse, Mesoamerican, Chinese, has tried to answer the question of what was before the beginning. The answers have taken the form of gods and creators, and cosmic eggs, and primordial waters, and the word of a deity spoken into void. These answers are not physics. But the question behind them is the same question that drives physicists to write the Wheeler-DeWitt equation and to search the CMB for the signatures of a prior aeon. The question is native to consciousness. It arises wherever there is a mind complex enough to understand the concept of a beginning. It arises in every culture, in every era, in every mind that looks honestly at its own existence and wonders how this, all of this, came to be. And the history of science has not made this question smaller. It has made it larger. Every advance in cosmology has pushed the boundary of the known further, but it has also pushed the boundary of the unknown further. and the unknown has expanded faster than the known. We know more than Newton about the origin of the universe. We also know more about how much more there is to know. This is the structure of understanding at the frontier. Every answer is simultaneously a discovery and an invitation to go deeper. The universe does not have a bottom. Or if it does, we have not found it. And the fact that we have been searching seriously, rigorously for over a century, using the most powerful mathematical and observational tools ever assembled, and have not found a bottom. This is not discouraging. It is one of the most remarkable and beautiful facts about the cosmos that we have discovered. What is before the Big Bang? Something we have no complete theory for. Something that may be a prior quantum state, or a timeless wave function, or a previous aeon, or a tunneling from nothing, or the wrong question entirely, reformulated. Something that points, at its most fundamental, to a layer of reality that is not made of space or time, or matter or energy, but of something we do not yet have words for. Something that gave rise to everything, and that, even if it cannot be named, is worth every moment of searching. 13 years and 8 months ago, in a hypothetical sense, in the time it would take to utter the words of this exploration, the universe has continued its expansion. Galaxies that were already impossibly far from each other are now fractionally farther. The cosmic microwave background has stretched to a slightly longer wavelength. The overall temperature of the universe has dropped by an amount so small it has no practical significance. And somewhere, almost certainly, a mind has been born into this cosmos and has looked up at the sky, perhaps for the first time, and felt the stirring of the oldest question. What was there before all of this? The answer that physics gives is not nothing. It is not something. It is, this question is still being worked on by the most serious and disciplined and imaginative minds our species has produced. And what we have found so far is that the question is deeper than we thought, that the universe is stranger than we imagined, and that the search itself, the sustained, rigorous, humble, awe-driven search, is one of the most distinctly and beautifully human things that has ever been done. Stay with this, because we are not done yet. The intellectual peak has been reached. Now the terrain changes. The questions do not stop, but they soften. The mathematics retreats, and what remains is the weight of what we have learned. The weight of uncertainty held honestly. The weight of wonder that does not require resolution to be genuine. There is a way in which all of cosmology and all of the before proposals we have examined converge on a single, quiet recognition. And it is this: the universe did not have to be here. Not in the theological sense, not as an argument for or against any particular religious claim. In the purely physical sense, there is no law of logic that requires a universe to exist. There is no equation that demands that something rather than nothing be the case. Every physical law we know of is a law about how things evolve if they exist, not a law that requires them to exist. Existence, in the deepest sense, is a brute fact. It is not explained by physics. It is assumed by physics. And yet, here we are. Here the universe is. 13.8 billion years old, vast beyond ordinary comprehension, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, containing at least one star with at least one planet on which the chemistry of carbon gave rise to self-replicating molecules, which gave rise to cells, which gave rise to organisms, which gave rise to nervous systems complex enough to model the world, which gave rise to the consciousness that is, at this moment, contemplating its own cosmic origin. The probability of this, if probability even applies to a single instance of existence, is not computable. But the fact of it is undeniable. You are here. The universe is here. And neither physics nor philosophy has yet explained with any finality why. That unresolved why is not a wound. It is not a failure of understanding. It is the permanent mark of genuine depth, the sign that something real and important is at stake. And it is the reason that the question of what came before the Big Bang is not merely an intellectual exercise for specialists, but one of the most profound questions that a conscious being can ask. Because it is, at bottom, the question of why there is a universe in which consciousness can arise and ask about its own origin. Why there is a cosmos that is not only here, but knowable, partially, tantalizingly, with ever-retreating boundaries. Why the universe is, as physicist Eugene Wigner famously noted in 1960, unreasonably effective at being described by mathematics. Why mathematics, abstract, timeless, discovered rather than invented, turns out to be the language in which physical reality is written. These questions cannot be separated from each other. They are different faces of the same mystery. And that mystery, vast, irreducible, beautiful, is the permanent companion of everyone who takes the questions seriously. Now the cooling comes. The questions do not disappear, but they change their register. From urgency to acceptance. From striving to dwelling. From the narrow focus of a problem being solved to the wide, soft focus of a mystery being inhabited. Stand on a hilltop at dusk, somewhere far from city lights. The sky is not yet fully dark. There is still a residue of blue at the western horizon, the last light of a star that is, at this moment, 93 million miles away. To the east, the first stars are appearing. Not appearing exactly, but becoming visible as the background light of the sky dims enough that their ancient photons can be distinguished from the glow of scattered sunlight. You are not seeing those stars as they are now. You are seeing them as they were decades or centuries ago, their light having traveled across interstellar space at 300,000 kilometers per second, arriving at your retina in this precise moment, this soft and particular dusk. Everything you see when you look up is the past. The farther you look, the deeper into time you reach. The night sky is a map of history, layered and luminous. Every point of light a different depth in time. And at the very edge of what any telescope can see, beyond the visible stars, beyond the distant galaxies, beyond the faint smear of the most remote structures, lies the cosmic microwave background, the oldest light in the universe, arriving from 380,000 years after the beginning, carrying the imprint of what the cosmos was like before a single star had formed. And behind that, behind the oldest light, that is what we have been descending toward. And now, having reached the bottom of the descent, having examined every serious scientific proposal for what lies beyond the CMB, beyond inflation, beyond the Planck wall, it is time to let the weight of what we have learned settle. Not to summarize it technically, but to feel it, to let it change the texture of standing on that hilltop, to let the questions we cannot answer become companions rather than problems. This is the place in the journey where the pace changes, where the velocity of ideas slows, not because there is nothing left to say, but because some things are better absorbed than argued. Some things need space around them. The universe is 13.8 billion years old. You have heard this number several times now, and by repetition, it may have begun to feel familiar, manageable, almost comfortable. Let it become strange again. 13.8 billion years. A billion is 1,000 millions. 13.8 billion years ago, the atoms that now constitute your body did not exist in any form that would be recognizable. The protons in your hydrogen atoms were freshly created, cooling from a plasma in which they had not yet found electrons to orbit. The heavier atoms, the carbon, nitrogen, oxygen, iron, did not exist at all. They would not exist until the first stars formed, hundreds of millions of years later, and fused hydrogen into helium, and helium into carbon, and carbon into oxygen in their stellar cores, and then exploded, scattering those elements across the galaxy, where they would eventually be gathered by gravity into a second generation of stars, and a third, and eventually into the solar system in which you live. You are a third-generation cosmic structure. You required 13.8 billion years of preparation. You required the deaths of multiple stars. You required the precise values of the physical constants, the fine structure constant, the cosmological constant, the mass of the electron, the strength of the strong nuclear force that allowed stars to burn steadily, that allowed carbon to be synthesized in stellar interiors rather than bypassed, that allowed galaxies to form and persist rather than flying apart or collapsing before any stars could form. All of that preparation, the full 13.8 billion years of it, is what lies between the question, what was before the Big Bang, and the existence of anyone to ask it. The question is not abstract. It is the question of your own deepest origin. And the answer, whatever it turns out to be, will describe the conditions that made your existence possible, not just in principle, but in this particular form, with these particular laws, at this particular moment in cosmic history. Picture yourself back on that hilltop, but now the sky is fully dark. The Milky Way is visible as a faint smear of light crossing the sky from one horizon to the other. You are looking at the disk of our galaxy, 100,000 light-years across, containing somewhere between 200 and 400 billion stars. You are inside it. You are part of it. The light from the stars at the galaxy's center left before our species existed. The light from the stars at its far edge left before our planet formed. The galaxy is so large that you cannot see it all at the same moment in time. The near edge and the far edge are separated not just by space, but by tens of thousands of years of cosmic history. Now pull back further. The Milky Way is one of roughly 2 trillion galaxies in the observable universe. Each galaxy contains hundreds of billions of stars. Each star has, on average, at least one planet. The observable universe, the sphere defined by how far light has had time to travel since the Big Bang, has a radius of roughly 46 billion light-years. And beyond the observable universe lies more universe, extending in all directions to distances we cannot probe, possibly infinite, possibly finite, but larger than any number we can meaningfully contemplate. All of this arose from a state of extraordinary density and heat 13.8 billion years ago, which was itself preceded by, we do not know, possibly a quantum bounce from a prior universe, possibly an eternal inflating space-time, possibly a tunneling from nothing, possibly something we have not yet imagined. The scale of what we do not know is, in its own way, as extraordinary as the scale of what we do. The observable universe contains roughly 10 to the 80 atoms. The number of possible quantum states of the observable universe is 10 to the 10 to the 123 by Penrose's estimate. The number of possible string theory vacua, the number of possible universes with different physical laws, may be 10 to the 500 or more. These are not numbers. They are gestures in the direction of the incomprehensible. And yet, one of those 10 to the 80 atoms is part of a finger that, at this moment, traces the outline of these questions in the dark. One arrangement of those atoms produces the experience of wondering where the atoms came from. The universe has, in one of its corners, folded itself into a shape that asks about its own origin. This is perhaps the most extraordinary thing about the universe. Not its size, not its age, not its complexity, but the fact that it has become, in at least one place, self-aware. Stay with this for a moment. It deserves its own space. We tend, in discussions of cosmology, to treat consciousness as a late arrival, something that evolved on a small planet around an ordinary star, billions of years into cosmic history, a local phenomenon of vanishing significance against the backdrop of the universe's vast scale. This may be true in terms of physical mass or spatial extent, but in terms of what consciousness does, in terms of its function, it is anything but peripheral. Consciousness is the only mechanism by which the universe knows itself. Without it, the quantum fluctuations in the CMB are patterns with no one to read them. The Big Bang is an event with no one to reconstruct it. The laws of physics are equations with no one to discover them. The question of what came before the beginning is a question with no one to ask it. You are the universe's way of wondering about itself. You, lying in the dark, listening to these words, following these ideas into the deepest questions physics and philosophy can generate. You are doing something that no other arrangement of matter in the observable universe is known to do. You are contemplating your own cosmic origin. You are attempting to understand the conditions of your own existence. This is not a small thing. It is, in fact, the thing that makes all of science and all of philosophy meaningful. Not because consciousness is separate from the physical universe, or supernatural, or exempt from explanation. It is not. Consciousness is physical, as far as we can tell, arising from the extraordinarily complex organization of matter in nervous systems that evolved through billions of years of natural selection. But the fact that physical processes can give rise to the experience of wondering about physical processes, the fact that matter can organize itself into a form that models the cosmos and asks where the cosmos came from, this is a genuine and profound feature of reality, not a footnote, and it connects directly to the before question in ways that are not often made explicit. Every serious proposal for what came before the Big Bang must, implicitly or explicitly, provide conditions under which a universe capable of harboring consciousness could arise. The no-boundary proposal produces a universe with smooth initial conditions, conditions that allow the formation of stars, planets, chemistry, biology. Loop quantum cosmology produces a bounce that launches a new expanding universe with a low entropy beginning, low enough for complexity to emerge. Conformal cyclic cosmology produces, at the transition between aeons, the low entropy smooth beginning that Penrose calculates is required for structure to form. Quantum tunneling from nothing produces a universe that, by the logic of anthropic selection, must be capable of containing observers, or we would not be here to observe it. In every case, the before that is proposed is constrained, implicitly or explicitly, by the fact that what came after was capable of producing us. This is sometimes called the anthropic constraint, and it is simultaneously the most and least satisfying feature of modern cosmology. Least satisfying because it seems circular. The universe is the way it is because it had to be capable of producing observers, and we know it had to be capable of producing observers because we are observing it. The reasoning appears to go nowhere. Most satisfying because it is actually saying something real. The before, whatever it was not arbitrary. It was constrained either by physical law or by selection to produce something. The universe did not arrive at us by accident in a space with no constraints. It arrived at us through a process, whatever that process was, that had specific properties, specific structure, specific mathematical character. And that structure, that character, that law-governed process, that is the before we are searching for. Now consider the emotional texture of this understanding. Not the intellectual content. We have examined that thoroughly. The emotional texture. You have spent your life inside a universe that you did not choose, that you were born into without consent, with laws you did not write and constants you cannot alter. The universe was handed to you, already running, already 13.8 billion years old, already furnished with stars and galaxies and the specific chemistry of carbon that makes your body possible. You have never stood outside it. You have never seen it from the outside. You will never be able to see it from the outside. And yet, you have, by the exercise of reason and mathematics and observation, been able to reconstruct, partially, imperfectly, with genuine uncertainties honestly acknowledged, the history of the universe from the first fraction of a second onward. You have been able to identify the Planck wall and name what lies on the other side, even if you cannot see through it. You have been able to generate serious, mathematically coherent proposals for what preceded the beginning. You have been able to trace the question of existence to the place where it cannot be answered. And in doing so, you have located, with precision, the limit of what is knowable. This is a form of knowledge that is different from the knowledge of facts. It is the knowledge of limits, self-knowledge of the most fundamental kind. The universe knowing, through you, where its own self-knowledge ends. There is something quietly extraordinary about that. It does not resolve anything. It does not provide the warm comfort of an answer. But it has a quality that is, if you attend to it carefully, its own kind of peace. The peace of honest confrontation with the real. The peace of having looked as far as looking can reach, and of accepting without despair that the horizon does not disappear, but simply recedes. The great physicist Richard Feynman once described the pleasure of not knowing as one of the deepest joys of scientific life. The ability to live with uncertainty, to sit with an open question, to resist the temptation of premature closure. He said, in essence, that not knowing something is far more interesting than having a wrong answer, because not knowing preserves the possibility of discovering what is actually true. The before the Big Bang question is, in this sense, one of the richest objects in all of human knowledge. It is a question that has been seriously asked for less than a century, that has been asked with mathematical precision for only a few decades, and that has already, in that short time, generated enough understanding to fill libraries and enough genuine mystery to fill the rest of the universe. It will not be resolved tomorrow. It may not be resolved in your lifetime or in any lifetime within what we can currently foresee, but it will be worked on. Physicists at the Perimeter Institute in Waterloo, at the Max Planck Institute in Potsdam, at Tufts University in Massachusetts, at the Indian Institute of Science Education and Research in Pune, at King's College London, at Caltech and Princeton and Cambridge and Beijing. They are, at this moment, writing equations, running computer simulations, analyzing CMB data, debating mathematical frameworks, looking for the signatures of what came before in the data that surrounds us. The question is alive. The search is real. And every step forward, every constraint placed on a prior cosmology by a CMB measurement, every loop quantum bounce confirmed in a symmetric model, every CDT simulation that reproduces the four-dimensional geometry of our universe, every anomaly in the CMB that hints at something beyond the standard picture, is a step toward a boundary that may never be fully crossed, but that is, step by step, being more precisely located. What came before the Big Bang? Something that gave rise to time, something that gave rise to space, something that gave rise to the laws that governed the quantum geometry of the first instant, something that set the initial entropy of the universe at the extraordinarily low value that allowed stars and planets and chemistry and biology and consciousness to emerge. Something that, whether it was a prior universe or a timeless wave function or a quantum bounce or a tunneling from nothing, was constrained in some way we do not yet understand to produce a universe in which this question could be asked. The answer is not nothing. The answer is not a simple prior state. The answer is, at its most honest, we are still finding out. And the finding out, the sustained, rigorous, humble, awe-filled search, is itself one of the most distinctly human things that has ever been done with the matter and energy that the Big Bang provided. Now we reach the final passage. The existential climax has been building through everything we have examined. And it arrives not with a bang, but with a recognition. A recognition so old that every culture has felt its edges, and so new that our best physics has only recently been able to locate it with precision. Consider what it means, historically, for a species to confront the question of its own cosmic origin. For most of human history, the question was answered by mythology and religion, by stories of gods who shaped the cosmos from chaos, of primordial waters from which land emerged, of a divine word spoken into void that caused existence to differentiate from nothingness. These stories are not arbitrary. They reflect genuine cognitive encounters with the question's depth, genuine attempts using the conceptual tools available to make sense of the extraordinary fact of existence. The Babylonian Enuma Elish, written perhaps 3,500 years ago in the ancient city of Babylon, on the banks of the Euphrates River in what is now Iraq, describes a time before the sky and the earth had been named, a time of primordial waters, undifferentiated, before any distinction had been made. The Greek philosophers of the 6th and 5th centuries B.C.E., Thales of Miletus, Anaximander, Anaximenes, proposed that the cosmos arose from a single fundamental substance, a primal stuff that differentiated into the diversity of the world. Anaximander proposed something he called the apeiron, the boundless, the indefinite, as the source from which all things arise and to which they return. Not water, not fire, not any particular thing, but the groundless ground from which all particular things emerge. There is something in Anaximander's apeiron that resonates, across 25 centuries, with what modern cosmology is groping toward when it describes the timeless wave function, or the quantum geometry from which space-time emerges, or the mathematical structure of all possible universes. The apeiron is not a physical substance. It is a conceptual gesture in the direction of something that is prior to all particular things, the condition for the possibility of anything at all. And that gesture, the attempt to name the unnameable ground of existence, is the same gesture that Hartley and Hawking made when they wrote the no-boundary wave function, that Ashtekar made when he traced the loop quantum bounce, that Penrose made when he identified the conformal structure that connects the death of one aeon to the birth of the next. The tools are different. The precision is incomparably greater. The mathematical sophistication is of a different order entirely. But the question is the same. The human mind, confronting the mystery of its own existence in a cosmos it did not choose, asking, what was before? What is the ground? What is the source? This continuity, from the banks of the Euphrates to the corridors of the Perimeter Institute, is one of the most moving facts in the history of thought. The question has never been abandoned. It has been refined, sharpened, technically elaborated, mathematically formalized, but never abandoned. Every civilization that has produced reflective minds has produced versions of this question. It is native to consciousness. It arises wherever awareness is complex enough to model its own existence. And this tells us something important. Not about the answer, about the question. The fact that this question has been asked across every culture, in every era, by every tradition of inquiry. This suggests that the question is not an artifact of any particular framework. It is not a question that arises only because of Greek philosophy, or modern physics, or Western intellectual tradition. It arises because it is the natural consequence of any mind complex enough to understand the concept of a beginning. It is the question that existence asks of itself through any mind that is sufficiently developed to ask. What came before the Big Bang? Everything we are, everything we know, everything that has ever happened in the history of conscious experience on this planet. Every thought and every feeling and every moment of beauty or sorrow or love that any human being has ever had. All of it arose from the conditions set in place by whatever was before the Big Bang, by the quantum state or the prior universe, or the timeless wave function, or the tunneling from nothing that produced the specific Big Bang, that produced the specific cosmos, that produced the specific planet, that produced the specific biology that produced you. Here, now, listening to these words in the dark. The before is not remote. It is intimate. It is the most intimate thing there is. It is the origin of every capacity you have to understand anything, to feel anything, to wonder about anything. And the fact that it is unknown, that it may be, in significant part, permanently unknown, does not diminish its intimacy. It deepens it. Because the unknown is not a wall, it is deep. And depth is not something to be conquered, but something to be inhabited. The depth of the before question, its irreducible structure of the cosmos itself, depth, is the depth that makes the question worth asking. It is the depth that has kept the best minds of every generation returning to it. It is the depth that will keep the best minds of every future generation returning to it. The universe is under no obligation to be comprehensible. This is something that every working physicist who has spent time at the frontier knows, not as a philosophical position, but as a daily experience. The universe is what it is, and our concepts are our concepts. And the match between them, the extraordinary, unreasonable match that allows mathematics to describe physical reality with such precision, is itself a mystery that sits alongside the mystery of what came before the Big Bang. That the universe is comprehensible at all, that its laws are mathematical, that its structure is accessible to reason, that the mind evolved to find food and avoid predators, turns out, astonishingly, to be capable of deriving the equations of general relativity and quantum field theory and loop quantum cosmology. This is not something that any theory of the universe's origin has yet explained. It is a fact that sits behind all the other facts, quietly astonishing, usually unexamined. Why should the universe be beautiful? Why should it be orderly? Why should the same mathematics that describes curves on a blackboard also describe the shape of space-time around a black hole? These questions have no answers within physics. They are the conditions that make physics possible. And they are the things that every scientist who has spent time at the frontier, Einstein, Dirac, Penrose, Hawking, Ashtekar, Vilenkin, has encountered with something very close to reverence. Not religious reverence necessarily, not the reverence of doctrine, but the reverence of honest confrontation with something that exceeds the categories available to describe it. The reverence of looking as far as looking can reach and feeling, at the edge of the visible, the presence of something that is not yet visible, something that is not nothing, but that is not yet anything we have words for. The universe began. Something was before it. We do not know what. We are looking. The looking is real. The not knowing is real. And the question, the ancient, indestructible, bottomless question, is the most real thing of all. Take a moment to look back at the path. We began at a clock on a wall. We began with the simple, familiar tick of a second hand, moving forward through time the way second hands always have, the way time always seems to move. From somewhere into somewhere else, from before into after, from what was into what is. And from that simple domestic moment, we descended. Layer by layer, scale by scale, concept by concept, we went down into the deepest question that a conscious being can ask about its own existence. We went through the cosmic microwave background, the oldest light in the universe, the surface of last scattering at 380,000 years after the beginning, the wall of photons beyond which no telescope can see. We went through inflation, the extraordinary exponential expansion that smoothed the universe and stretched quantum fluctuations into the seeds of cosmic structure, driven by Alan Guth's inflaton field and elaborated by Andrei Linde and Alexander Vilenkin into the vast, eternal, self-reproducing, inflationary multiverse. We went through the Border-Guth-Vilenkin theorem, which showed that even eternal inflation cannot extend infinitely into the past, that every expanding space-time has a boundary, a beginning that it cannot think its way out of. We went through the Planck wall, the 10 to the negative 43 seconds, the scale at which general relativity and quantum mechanics are simultaneously required and simultaneously incompatible, the place where every equation currently available to physics either breaks down or requires assumptions that have not been tested. We went through the Hartley-Hawking no-boundary proposal, the shuttlecock-shaped universe in which imaginary time replaces the singular beginning with a smooth, rounded geometry, in which asking what was before the Big Bang is like asking what is south of the South Pole, in which time itself is not a precondition of existence, but an emergent feature of a quantum state that is, at its deepest level, timeless. We went through the loop quantum bounce, the quantum geometric repulsion discovered in 2006 by Abhay Ashtekar, Tomasz Pawlowski, and Parampreet Singh at Pennsylvania State University, which replaces the classical singularity with a moment of maximum density from which a prior universe rebounds into ours, making the Big Bang not a beginning, but a transition, not a creation, but a transformation. We went through Roger Penrose's conformal cyclic cosmology, the vision of infinite eons, each beginning with a Big Bang and ending in a cold, massless expanse, conformally equivalent to the next aeon's beginning, each dying universe becoming the birth condition of the next, the death of stars and galaxies, and black holes converted, through the mathematics of conformal rescaling, into the low-entropy, smooth beginning of a new cosmos. We went through the CPT symmetric universe, the quantum tunneling from nothing, the causal dynamical triangulations, the holographic principle, and the emergence of space-time from quantum entanglement. We went through the Wheeler-DeWitt equation, that astonishing, timeless equation, written by Bryce DeWitt and John Wheeler in the late 1960s, which describes the quantum state of the universe without any time parameter, which suggests that the universe at its most fundamental level, does not evolve in time, because time is not fundamental but emergent, a statistical property of a quantum system viewed from the inside. We went through the problem of time in quantum gravity, through relational time and the emergence of temporal experience from the correlations between physical subsystems in a universe that is globally frozen. We went through the string landscape, the 10 to the 500 possible configurations of compactified extra dimensions, each giving rise to a different set of physical laws, each corresponding to a different possible universe in the inflationary multiverse. We went through the fine-tuning problem and the anthropic principle. We went through Leibniz's question: why is there something rather than nothing? And through the recognition that every answer physics has proposed to that question is itself something that requires explanation, that the regress does not terminate within physics, that the conditions for the possibility of physics cannot be explained by physics. And we went through the recognition, quiet, enormous, irreducible, that the question of what came before the Big Bang is the question of the origin of everything, of time and space and law and consciousness and the capacity to wonder, of you, here, now, in the dark, carrying 13.8 billion years of cosmic preparation in every atom of your body. That is the path we have walked, and now we have returned to its beginning. Look at the clock on your wall. The second hand is still moving. It is doing what it has always done, marking the passage of moments, dividing the continuous flow of time into discrete countable units, making the invisible river of becoming visible and measurable. It moves forward, and it has always moved forward, and there is something so ordinary and so reliable about it that it is easy to forget what an extraordinary thing it is doing. It is marking the passage of time in a universe that 13.8 billion years ago may not have had time to mark. It is performing a measurement that requires a measurer in a cosmos that, for the vast majority of its history, contained no measurers. It is doing something that is only possible because the Big Bang happened, and because inflation happened, and because the quantum fluctuations of the early universe happened to be at the right amplitude to seed the formation of galaxies, and because one of those galaxies happened to contain a star with the right mass to burn steadily for 5 billion years, and because one of that star's planets happened to be at the right distance to maintain liquid water, and because the chemistry of that planet happened to produce self-replicating molecules, and because 4 billion years of evolution happened to produce a nervous system capable of building a clock and reading it and wondering what was happening before clocks existed. Every tick of that second hand is the product of everything we have explored. Every moment of your experience is downstream of the question we have been asking. The question and the asker are not separate things. You are the universe's way of encountering its own origin. Not from outside, not with perfect knowledge, not with the detachment of an observer who preceded the phenomenon being observed, but from inside, embedded, partial, limited, and for all of that, genuinely and irreplaceably here. What was there before the Big Bang? If the Hartle-Hawking no-boundary proposal is correct, the question is beautifully, geometrically malformed. Not wrong, but inapplicable, the way south is inapplicable at the South Pole. The universe had no before, not because it was always here in its current form, but because the concept of temporal precedence does not apply to the quantum geometry from which time itself emerged. The second hand on your clock is moving through a time that began, not in the sense that something was there before it, but in the sense that the concept of before was part of what began. If loop quantum cosmology is correct, there was a universe before ours, a universe that contracted, that reached the Planck density, that rebounded through the quantum geometric repulsion that Ashtekar and colleagues discovered, and that gave way to our expansion. That prior universe had its own history, its own structures, its own arrow of time. Its death was our birth. And before that universe, perhaps, was another, and before that, another still, in a sequence that may be infinite in both directions, an eternal rhythm of contraction and expansion, each cycle carrying forward some faint quantum memory of what came before, most of it washed away by the violence of the bounce. If conformal cyclic cosmology is correct, our universe will itself become the before of a future cosmos. The stars we can see tonight are not permanent. They will burn out, one by one, over timescales incomprehensible in human terms, leaving white dwarfs that cool to blackness, neutron stars that slowly radiate away their energy, black holes that evaporate through Hawking radiation over 10 to the 100th power years. And when the last black hole has evaporated, when the last massive particle has dispersed, when the universe is nothing but an infinite cold ocean of photons and gravitational waves, in that unimaginably distant future, the geometry of our dying universe will become conformally equivalent to the beginning of the next. Our end will be someone else's beginning. The clock on your wall is ticking in an aeon that will one day be the before of an aeon that does not yet exist. If quantum tunneling from nothing is correct, if Vilenkin's proposal captures something real about the deepest layer of physical reality, then there was no prior state at all. The universe came into being, not from something, but from the quantum possibility of something, from the mathematical structure of a wave function defined on a space of possible configurations. Before the universe, there was only the logic of quantum mechanics, not a physical logic, not a logic embedded in space-time, but the pure mathematical structure of what is possible. And from that pure possibility, through the quantum process that needs no cause and no prior time, our universe emerged. If space-time is emergent from quantum entanglement, if the holographic principle extends to our de Sitter universe, if the geometry of the cosmos is a large-scale approximation to a more fundamental pattern of quantum information, then before the Big Bang was not a prior state of space-time, but a prior state of something more fundamental, of entanglement patterns without a spatial context, of quantum degrees of freedom without a geometric organization, of information that had not yet organized itself into the four-dimensional structure we call space and time. The before was not empty space. It was not the quantum vacuum. It was the condition prior to the emergence of space itself, the quantum substrate from which geometry crystallized as the universe cooled through the Planck era. We do not know which of these is correct. We may not know for a very long time. We may never know with certainty, because certainty may not be available at the Planck scale, because the information about what came before may have been erased by inflation, because the question may be touching a layer of reality that is permanently beyond the reach of any instrument or theory built from within the universe being examined. And yet, and this is the most important thing, the not knowing is not emptiness. The not knowing is full. It is full of the most serious and sustained intellectual effort that human beings have directed at any single question. It is full of the Wheeler-DeWitt equation and the loop quantum bounce and the conformal cyclic cosmology and the no-boundary wave function and the string landscape and the causal dynamical triangulations. It is full of the CMB maps produced by WMAP and Planck, of the bicep and Keck array experiments at the South Pole, searching for the polarization signature of primordial gravitational waves, of the James Webb Space Telescope probing the earliest galaxies, of the numerical relativity simulations being developed by Eugene Lim and Katie Clough, and Yosu Orikuetsea to peer into the extreme conditions near the Big Bang. It is full of the work being done right now, tonight, in offices and laboratories and seminar rooms around the world, by people who have dedicated their intellectual lives to pushing the boundary of the known one equation further into the unknown. The not knowing is the sign of a living question. A dead question has been answered, filed away, closed. A living question breathes. It generates new approaches, new frameworks, new predictions, new reasons to look at old data differently. The before the Big Bang question has never been more alive than it is right now. Not because we are close to answering it, but because we are closer than we have ever been to understanding precisely what it is asking and precisely what it would take to answer it. This is worth something. In fact, it is worth everything. Leibniz asked his question, why is there something rather than nothing? In 1714, in a universe that was still thought to be a few thousand years old, in which the concept of a Big Bang was more than 2 centuries away. He asked it without the tools to make progress on it, and he knew it. He asked it because the question is real, and because asking even without the answer is itself an act of the highest intellectual seriousness. Every physicist and cosmologist who has spent their career working on the questions we have explored tonight is doing what Leibniz did, asking a question whose full answer may be beyond reach, because the asking is how understanding advances. Because each generation's incomplete answer becomes the next generation's starting point. Because the boundary of the known moves, slowly, through the sustained effort of minds that refuse to accept the first comfortable answer as the final one. What was there before the Big Bang? In the end, in this end, this synthesis, this return to the beginning, the most honest and the most complete answer is this: a question. A question so deep that it cannot be answered from within the universe it is asking about. A question so fundamental that every attempt to answer it reveals a new layer of the mystery beneath. A question so ancient that every civilization that has produced reflective minds has produced some version of it. A question so modern that it is currently being worked on by some of the finest mathematical physicists alive, using instruments and frameworks that did not exist a generation ago. And a question so personal, so intimate, so inseparable from the existence of the one asking it, that it is not, in the end, a question about the remote past. It is a question about right now, about what it means to be here in a universe that exists, that has laws, that has a history, that produced the conditions for consciousness, that folded itself into a shape that can wonder about its own origin. The clock on your wall is still ticking. The second hand is still moving. The room around you is still dark or dim, or beginning to lighten with the first suggestion of dawn. Your breath is moving in and out. Your body is here. The atoms of your body, carbon, hydrogen, oxygen, nitrogen, iron, are here 13.8 billion years after the quantum event that produced the first hydrogen, 5 billion years after the stellar deaths that produced everything heavier. You are here. The universe is here. The question is here. And behind the question, deeper than any answer we currently possess, deeper than any theory we have so far constructed, deeper than the Planck wall and the CMB horizon, and the inflationary epoch and the quantum bounce, and the no-boundary wave function, behind all of it, the very bottom of the descent we have made together, there is something. Not nothing. Something. Something that we have not yet named, not yet understood, not yet even correctly described. Something that was the condition for time and space and law and consciousness and wondering. Something that, For now, we can only gesture toward with questions. If this changed how you think about time, about the universe, about the extraordinary fact of your own existence within it, then the hours we have spent descending together were well spent. The question will not leave you. It should not leave you. It is the right question to carry. The most honest and the most important question a conscious being in this particular cosmos can ask. Thank you for staying. Thank you for listening, for following the ideas into the deepest places they go, for tolerating the uncertainty and the complexity and the honest admission that we do not know. That willingness to sit with the unknown, to resist the false comfort of premature closure, to keep looking even when looking reveals only deeper mystery. That is the most distinctly human response to the universe that I know of. The second hand moves forward. It has always moved forward. And somewhere behind the first forward, there is something we are still finding words for.